Preface, Contents, and Introduction for the Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Preface. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898-1899. The results of his investigation were rearranged and put into the form in which they appear here as a memorial address published in connection with the celebration at the unveiling of the Gauss-Weber monument at Göttingen in June 1899. In the French edition, which appeared soon after, Professor Hilbert made some additions, particularly in the concluding remarks, where he gave an account of the results of a recent investigation made by Dr. Dane. These additions have been incorporated in the following translation. As a basis for the analysis of our intuition of space, Professor Hilbert commences his discussion by considering three systems of things, which he calls points, straight lines, and planes, and sets up a system of axioms connecting these elements in their mutual relations. The purpose of his investigations is to discuss systematically the relations of these axioms to one another, and also the bearing of each upon the logical development of Euclidean geometry. Among the important results obtained, the following are worthy of special mention. 1. The mutual independence and also the compatibility of the given system of axioms is fully discussed by the aid of various new systems of geometry which are introduced. 2. The most important propositions of Euclidean geometry are demonstrated in such a manner as to show precisely what axioms underlie and make possible the demonstration. 3. The axioms of congruence are introduced and made the basis of the definition of geometric displacement. 4. The significance of several of the most important axioms and theorems in the development of the Euclidean geometry is clearly shown. For example, it is shown that the whole of the Euclidean geometry may be developed without the use of the axiom of continuity. The significance of Desargues' theorem as a condition that a given plane geometry may be regarded as a part of a geometry of space is made apparent, etc. 5. A variety of algebras of segments are introduced in accordance with the laws of arithmetic. This development and discussion of the foundation principles of geometry is not only of mathematical, but of pedagogical importance. Hoping that through an English edition, these important results of Professor Hilbert's investigation may be made more accessible to English-speaking students and teachers of geometry, I have undertaken, with his permission, this translation. In its preparation, I have had the assistance of many valuable suggestions from Professor Osgood of Harvard, Professor Moore of Chicago, and Professor Halstead of Texas. I am also under obligations to Mr. Henry Corr and Mr. Arthur Bell for reading the proof. E. J. Townsend, University of Illinois. Contents. Introduction. Chapter 1. The 5 Groups of Axioms. Section 1. The Elements of Geometry and the 5 Groups of Axioms. Section 2. Group 1. Axioms of Connection. Section 3. Group 2. Axioms of Order. Section 4. Consequences of the axioms of connection and order. Section 5. Group 3. Axiom of parallels, Euclid's axiom. Section 6. Group 4. Axioms of congruence. Section 7. Consequences of the axioms of congruence. Section 8. Group 5. Axiom of continuity, Archimedes' axiom. Chapter 2. The compatibility and mutual independence of the axioms. Section 9. Compatibility of the axioms. Section 10. Independence of the axioms of parallels, non-euclidean geometry. Section 11. Independence of the axioms of congruence. Section 12. Independence of the axiom of continuity, non-archimedean geometry. Chapter 3. The theory of proportion. Section 13. Complex number systems. Section 14. Demonstration of Pascal's theorem. Section 15. An algebra of segments based upon Pascal's theorem. Section 16. Proportion and the theorems of similitude. Section 17. Equations of straight lines and of planes. Chapter 4. The theory of plane areas. Section 18. Equal area and equal content of polygons. Section 19. Parallelograms and triangles having equal bases and equal altitudes. Section 20. The measure of area of triangles and polygons. Section 21. Equality of content and the measure of area. Chapter 5. Desargues' theorem. Section 22. Desargues' theorem and its demonstration for plane geometry by aid of the axioms of congruence. Section 23. The impossibility of demonstrating Desargues' theorem for the plane without the help of the axioms of congruence. Section 24. Introduction of an algebra of segments based upon Desargues' theorem and independent of the axioms of congruence. Section 25. The commutative and the associative law of addition for our new algebra of segments. Section 26. The associative law of multiplication and the two distributive laws for the new algebra of segments. Section 27. Equation of the straight line based upon the new algebra of segments. Section 28. The totality of segments regarded as a complex number system. Section 29. Construction of a geometry of space by aid of a Desarguesian number system. Section 30. Significance of Desargues' theorem. Chapter 6. Pascal's theorem. Section 31. Two theorems concerning the possibility of proving Pascal's theorem. Section 32. The commutative law of multiplication for an Archimedean number system. Section 33. The commutative law of multiplication for a non-Archimedean number system. Section 34. Proof of the two propositions concerning Pascal's theorem, Non-pascalian geometry. Section 35. The demonstration by means of the theorems of Pascal and Desargues of any theorem relating to points of intersection. Chapter 7. Geometrical constructions based upon the axioms 1 through 5. Section 36. Geometrical constructions by means of a straight edge and a transferer of segments. Section 37. Analytical representation of the coordinates of points, which can be so constructed. Section 38. The representation of algebraic numbers and of integral rational functions as sums of squares. Section 39. Criterion for the possibility of a geometrical construction by means of a straight edge and a transferer of segments. Conclusion. All human knowledge begins with intuitions, thence passes to concepts, and ends with ideas. Kant, Kritik der reinen Vernunft, Elementariera, Part 2, Section 2. Introduction. Geometry, like arithmetic, requires for its logical development only a small number of simple fundamental principles. These fundamental principles are called the axioms of geometry. The choice of the axioms and the investigation of their relations to one another is a problem which, since the time of Euclid, has been discussed in numerous excellent memoirs to be found in the mathematical literature. This problem is tantamount to the logical analysis of our intuition of space. The following investigation is a new attempt to choose for geometry a simple and complete set of independent axioms, and to deduce from these the most important geometrical theorems in such a manner as to bring out as clearly as possible the significance of the different groups of axioms and the scope of the conclusions to be derived from the individual axioms. End of preface, contents, and introduction. Chapter 1, Section 1 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. The 5 Groups of Axioms. Section 1. The Elements of Geometry and the 5 Groups of Axioms. Let us consider 3 distinct systems of things. The things composing the first system we will call points and designate them by the capital letters A, B, C, ... And those of the second we will call straight lines and designate them by the lowercase letters A, B, C, ... And those of the third system we will call planes and designate them by the Greek letters alpha, beta, gamma, ... The points are called the elements of linear geometry, the points and straight lines the elements of plane geometry, and the points, lines, and planes the elements of the geometry of space, or the elements of space. We think of these points, straight lines, and planes as having certain mutual relations, which we indicate by means of such words as are situated, between, parallel, congruent, continuous, etc. The complete and exact description of these relations follows as a consequence of the axioms of geometry. These axioms may be arranged in 5 groups. Each of these groups expresses, by itself, certain related fundamental facts of our intuition. We will name these groups as follows. Roman numeral 1, 1 through 7, axioms of connection. Roman numeral 2, 1 through 5, axioms of order. Roman numeral 3, axiom of parallels, Euclid's axiom. Roman numeral 4, 1 through 6, axioms of congruence. Roman numeral 5, axiom of continuity, Archimedes' axiom. End of chapter 1. Chapter 1, Section 2 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 2, Group 1, Axioms of Connection. The axioms of this group establish a connection between the concepts indicated above, namely points, straight lines, and planes. These axioms are as follows. 1, 1. Two distinct points A and B always completely determine a straight line A. We write AB equals A or BA equals A. Instead of determine, we may also employ other forms of expression. For example, we may say A lies upon A. A is a point of A. A goes through A and through B. A joins A and or with B, etc. If A lies upon A and at the same time upon another straight line B, we make use also of the expression, the straight lines A and B have the point A in common, etc. 1, 2. Any two distinct points on a straight line completely determine that line. That is, if AB equals A and AC equals A, where B is not equal to C, then is also BC equal A. 1, 3. 3 points A, B, C, not situated in the same straight line, always completely determine a plane alpha. We write ABC equals alpha. We employ also the expressions A, B, C lie in alpha. A, B, C are points of alpha, etc. 1, 4. Any 3 points A, B, C of a plane alpha which do not lie in the same straight line completely determine that plane. 1, 5. If 2 points A, B of a straight line A lie in a plane alpha, then every point of A lies in alpha. In this case, we say the straight line A lies in the plane alpha, etc. 1, 6. If 2 planes alpha, beta have a point A in common, then they have at least a second point B in common. 1, 7. Upon every straight line there exist at least 2 points. In every plane at least 3 points not lying in the same straight line. And in space there exist at least 4 points not lying in a plane. Axioms 1 through 2 contain statements concerning points and straight lines only, that is, concerning the elements of plane geometry. We call them, therefore, the plane axioms of Group 1, in order to distinguish them from the axioms 1, 3 through 7, which we designate briefly as the space axioms of this group. Of the theorems which follow from the axioms 1, 3 through 7, we shall mention only the following. Theorem 1. 2 straight lines of a plane have either 1 point or no point in common. 2 planes have no point in common or a straight line in common. A plane and a straight line not lying in it have no point or 1 point in common. Theorem 2. Through a straight line and a point not lying in it, or through 2 distinct straight lines having a common point, one and only one plane may be made to pass. End of section 2. Chapter 1. Section 3 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 3. Group 2. Axioms of Order. The axioms of this group define the idea expressed by the word between and make possible, upon the basis of this idea, an order of sequence of the points upon a straight line in a plane and in space. The points of a straight line have a certain relation to one another, which the word between serves to describe. The axioms of this group are as follows. 2, 1. If A, B, C are points of a straight line, and B lies between A and C, then B lies also between C and A. 2, 2. If A and C are 2 points of a straight line, then there exists at least one point B lying between A and C, and at least one point D so situated that C lies between A and D. 2, 3. Of any 3 points situated on a straight line, there is always one and only one which lies between the other 2. 2, 4. Any 4 points A, B, C, D of a straight line can always be arranged that B shall lie between A and C, and also between A and D, and furthermore, that C shall lie between A and D, and also between B and D. Definition. We will call the system of 2 points A and B lying upon a straight line a segment, and denote it by AB or BA. The points lying between A and B are called the points of the segment AB, or the points lying within the segment AB. All other points of the straight line are referred to as the points lying outside the segment AB. The points A and B are called the extremities of the segment AB. 2,5. Let ABC be 3 points not lying in the same straight line, and that A be a straight line lying in the plane ABC, and not passing through any of the points A, B, C. Then, if the straight line A passes through a point of the segment AB, it will also pass through either a point of the segment BC or a point of the segment AC. Axioms 2, 1 through 4 contain statements concerning the points of a straight line only, and hence we will call them the linear axioms of group 2. Axiom 2, 5 relates to the elements of plane geometry, and consequently shall be called the plane axiom of group 2. End of section 3. Chapter 1, Section 4, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 4. Consequences of the Axioms of Connection and Order. By the aid of the 4 linear axioms 2, 1 through 4, we can easily deduce the following theorems. Theorem 3. Between any 2 points of a straight line, there always exists an unlimited number of points. Theorem 4. If we have given any finite number of points situated upon a straight line, we can always arrange them in a sequence A, B, C, D, E, K, so that B shall lie between A and C, D, E, K, C between AB and DE, K, D between ABC and E, K, etc. Aside from this order of sequence, there exists but one other possessing this property, namely the reverse order K, EDCBA. Theorem 5. Every straight line A, which lies in a plane alpha, divides the remaining points of this plane into 2 regions having the following properties. Every point A of the one region determines with each point B of the other region a segment AB containing a point of the straight line A. On the other hand, any 2 points A prime of the same region determine a segment A prime containing no point of A. If A prime OB are 4 points of a straight line A, where O lies between A and B but not between A and A prime, then we may say the points A prime are situated on the line A upon one and the same side of the point O, and the points AB are situated on the straight line A upon different sides of the point O. All of the points of A which lie upon the same side of O, when taken together, are called the half-ray emanating from O. Hence, each point of a straight line divides it into 2 half-rays. Making use of the notation of Theorem 5, we say the points A prime lie in the plane alpha upon one and the same side of the straight line A, and the points A, B lie in the plane alpha upon different sides of the straight line A. Definitions. A system of segments AB, BC, CD, ... KL is called a broken line joining A with L and is designated briefly as the broken line ABCDE ... KL. The points lying within the segments AB, BC, CD ... KL, as also the points A, B, C, D ... KL, are called the points of the broken line. In particular, if the point A coincides with L, the broken line is called a polygon and is designated as the polygon ABCD ... K. The segments AB, BC, CD ... KA are called the sides of the polygon, and the points A, B, C, D ... K the vertices. Polygons having 3, 4, 5 ... n vertices are called respectively triangles, quadrangles, pentagons ... n-gons. If the vertices of a polygon are all distinct and none of them lie within the segments composing the sides of the polygon, and furthermore, if no two sides have a point in common, then the polygon is called a simple polygon. With the aid of Theorem 5, we may now obtain, without serious difficulty, the following theorems. Theorem 6. Every simple polygon, whose vertices all lie in a plane alpha, divides the points of this plane, not belonging to the broken line constituting the sides of the polygon, into two regions, an interior and an exterior, having the following properties. If A is a point of the interior region, interior point, and B a point of the exterior region, exterior point, then any broken line joining A and B must have at least one point in common with the polygon. If, on the other hand, A prime are 2 points of the interior and B prime 2 points of the exterior region, then there are always broken lines to be found joining A with A prime and B with B prime without having a point in common with the polygon. There exist straight lines in the plane alpha which lie entirely outside of the given polygon, but there are none which lie entirely within it. Theorem 7. Every plane alpha divides the remaining points of space into two regions having the following properties. Every point A of the one region determines with each point B of the other region a segment AH within which lies a point of alpha. On the other hand, any 2 points A prime lying within the same region determine a segment A prime containing no point of alpha. Making use of the notation of Theorem 7, we may now say the points A prime are situated in space upon one and the same side of the plane alpha, and the points A, B are situated in space upon different sides of the plane alpha. Theorem 7 gives us the most important facts relating to the order of sequence of the elements of space. These facts are the results, exclusively, of the axioms already considered, and hence no new space axioms are required in Group 2. End of Section 4. Chapter 1, Section 5 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 5, Group 3, Axioms of Parallels, Euclid's Axiom. The introduction of this axiom simplifies greatly the fundamental principles of geometry and facilitates in no small degree its development. This axiom may be expressed as follows. 3. In a plane alpha, there can be drawn through any point A, lying outside of a straight line A, one and only one straight line which does not intersect the line A. This straight line is called the parallel to A through the given point A. This statement of the axiom of parallels contains two assertions. The first of these is that, in the plane alpha, there is always a straight line passing through A which does not intersect the given line A. The second states that only one such line is possible. The latter of these statements is the essential one, and it may also be expressed as follows. Theorem 8. If two straight lines A, B of a plane do not meet a third straight line C of the same plane, then they do not meet each other. 4. If A, B had a point A in common, there would then exist in the same plane with C two straight lines A and B, each passing through the point A and not meeting the straight line C. This condition of affairs is, however, contradictory to the second assertion contained in the axiom of parallels as originally stated. Conversely, the second part of the axiom of parallels, in its original form, follows as a consequence of Theorem 8. The axiom of parallels is a plain axiom. End of section 5. Chapter 1, Section 6 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 6, Group 4. Axioms of Congruence. The axioms of this group define the idea of congruence or displacement. Segments stand in a certain relation to one another, which is described by the word congruent. 4,1. If A, B are 2 points on a straight line A, and if A' is a point upon the same or another straight line A', then upon a given side of A' on the straight line A', we can always find one and only one point B', so that the segment AB, or BA, is congruent to the segment A'B'. We indicate this relation by writing AB congruent to A'B'. Every segment is congruent to itself. That is, we always have AB congruent to AB. We can state the above axiom briefly by saying that every segment can be laid off upon a given side of a given point of a given straight line in one and only one way. 4,2. If a segment AB is congruent to the segment A'B', and also to the segment A'B', then the segment A'B' is congruent to the segment A'B'. That is, if AB is congruent to A'B', and AB is congruent to A'B', then A'B' is congruent to A'B'. 4,3. Let AB and BC be 2 segments of a straight line A, which have no points in common aside from the point B, and furthermore let A'B' and B'C' be 2 segments of the same or of another straight line A' having, likewise, no point other than B' in common. Then, if AB is congruent to A'B' and BC is congruent to B'C', we have AC congruent to A'C'. Definitions. Let alpha be any arbitrary plane, and HK any 2 distinct half-rays lying in alpha, and emanating from the point O, so as to form a part of 2 different straight lines. We call the system formed by these 2 half-rays HK an angle, and represent it by the symbol angle HK or angle KH. From Axioms 2, 1 through 5, it follows readily that the half-rays H and K, taken together with the point O, divide the remaining points of the plane alpha into 2 regions having the following property. If A is a point of one region and B a point of the other, then every broken line joining A and B either passes through O or has a point in common with one of the half-rays hk. If, however, A prime both lie within the same region, then it is always possible to join these 2 points by a broken line which neither passes through O nor has a point in common with either of the half-rays hk. One of these 2 regions is distinguished from the other in that the segment joining any 2 points of this region lies entirely within the region. The region so characterized is called the interior of the angle hk. To distinguish the other region from this, we call it the exterior of the angle hk. The half-rays h and k are called the sides of the angle, and the point O is called the vertex of the angle. 4,4. Let an angle hk be given in the plane alpha, and let a straight line A' be given in a plane alpha prime. Suppose also that, in the plane alpha, a definite side of the straight line A' be assigned. Denote by H' a half-ray of the straight line A' emanating from a point O' of this line. Then in the plane alpha prime there is one and only one half-ray K', such that the angle HK or KH is congruent to the angle H'K', and at the same time all interior points of the angle H'K' lie upon the given side of A'. We express this relation by means of the notation angle HK congruent to angle H'K'. Every angle is congruent to itself, that is, the angle HK is congruent to the angle HK, or the angle HK is congruent to the angle KH. We say, briefly, that every angle in a given plane can be laid off upon a given side of a given half-ray in one and only one way. 4,5. If the angle HK is congruent to the angle H'K' and to the angle H'K', then the angle H'K' is congruent to the angle H'K'. That is to say, if the angle HK is congruent to the angle H'K' and the angle HK is congruent to the angle H'K', then the angle H'K' is congruent to the angle H'K'. Suppose we have a given triangle ABC. Denote by HK the 2 half-rays emanating from A and passing respectively through B and C. The angle HK is then said to be the angle included by the sides AB and AC, or the one opposite to the side BC in the triangle ABC. It contains all the interior points of the triangle ABC and is represented by the symbol angle BAC or by angle A. 4,6. If in the 2 triangles ABC and A'B', the congruences AB congruent to A'B', AC congruent to A'C', the angle BAC congruent to the angle B'A'C' hold, then the congruences the angle ABC congruent to the angle A'B'C' and the angle ACB congruent to the angle A'C', also hold. Axioms 4, 1 through 3 contain statements concerning the congruence of segments of a straight line only. They may, therefore, be called the linear axioms of group 4. Axioms 4, 4, 5 contain statements relating to the congruence of angles. Axiom 4, 6 gives the connection between the congruence of segments and the congruence of angles. Axioms 4, 4 through 6 contain statements regarding the elements of plane geometry and may be called the plane axioms of group 4. End of section 6. Chapter 1, Section 7 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 7. Consequences of the Axioms of Congruence. Suppose the segment AB is congruent to the segment A'B'. Since, according to the axiom 4,1, the segment AB is congruent to itself, it follows from axiom 4,2 that A'B' is congruent to AB. That is to say, if AB is congruent to A'B', then A'B' is congruent to AB. We say, then, that the two segments are congruent to one another. Let A, B, C, D, KL, and A'B', C', D', K'L' be two series of points on the straight lines A and A' respectively, so that all the corresponding segments AB and A'B', AC and A'C', BC and B'C', KL and K'L' are respectively congruent. Then the two series of points are said to be congruent to one another. A and A', B and B', L and L' are called corresponding points of the two congruent series of points. From the linear axioms 4, 1 through 3, we can easily deduce the following theorems. Theorem 9. If the first of two congruent series of points, A, B, C, D, KL, and A'B', C', D', K'L' is so arranged that B lies between A and C, D, KL, and C between AB and D, KL, etc., then the points A', B', C', D', K'L' of the second series are arranged in a similar way. That is to say, B' lies between A' and C', D', K'L', and C' lies between A', B' and D', K'L', etc. Let the angle HK be congruent to the angle H'K'. Since, according to axiom 4,4, the angle HK is congruent to itself, it follows from axiom 4,5 that the angle H'K' is congruent to the angle HK. We say, then, that the angles HK and H'K' are congruent to one another. Definitions. Two angles having the same vertex and one side in common, while the sides not common form a straight line, are called supplementary angles. Two angles having a common vertex and whose sides form straight lines are called vertical angles. An angle which is congruent to its supplementary angle is called a right angle. Two triangles A, B, C, and A', B', C' are said to be congruent to one another when all of the following congruences are fulfilled. AB congruent to A', B', AC congruent to A', C', BC congruent to B', C', the angle A congruent to the angle A', the angle B congruent to the angle B', the angle C congruent to the angle C'. Theorem 10. First theorem of congruence for triangles. If for the two triangles ABC and A', B', C', the congruences AB congruent to A', B', AC congruent to A', C', the angle A congruent to the angle A' hold, then the two triangles are congruent to each other. Proof. From axiom 4, 6, it follows that the two congruences, the angle B congruent to the angle B prime and the angle C congruent to the angle C prime, are fulfilled, and it is, therefore, sufficient to show that the two sides, BC and B prime C prime, are congruent. We will assume the contrary to be true, namely that BC and B prime C prime are not congruent, and show that this leads to a contradiction. We take upon B prime C prime a point D prime such that BC is congruent to B prime D prime. The two triangles ABC and A prime B prime D prime have, then, two sides and the included angle of the one agreeing, respectively, to two sides and the included angle of the other. It follows from axiom 4, 6 that the two angles BAC and B prime A prime D prime are also congruent to each other. Consequently, by the aid of axiom 4, 5, the two angles B prime A prime C prime and B prime A prime D prime must be congruent. This, however, is impossible, since by axiom 4, 4, an angle can be laid off in one and only one way on a given side of a given half-ray of a plane. From this contradiction, the theorem follows. We can also easily demonstrate the following theorem. Theorem 11, second theorem of congruence for triangles. If in any two triangles, one side and the two adjacent angles are respectively congruent, the triangles are congruent. We are now in a position to demonstrate the following important proposition. Theorem 12. If two angles ABC and A prime B prime C prime are congruent to each other, their supplementary angles CBD and C prime B prime D prime are also congruent. Proof: take the points A prime C prime D prime upon the sides passing through B prime in such a way that A prime B prime is congruent to AB, C prime B prime congruent to CB, D prime B prime congruent to DB. Then, in the two triangles ABC and A prime B prime C prime, the sides AB and BC are respectively congruent to A prime B prime and C prime B prime. Moreover, since the angles included by these sides are congruent to each other by hypothesis, it follows from Theorem 10 that these triangles are congruent. That is to say, we have the congruences AC congruent to A prime C prime, the angle BAC congruent to the angle B prime A prime C prime. On the other hand, since by Theorem 4, 3, the segments AD and A prime D prime are congruent to each other, it follows, again from Theorem 10, that the triangles CAD and C prime A prime D prime are congruent, and consequently, we have the congruences CD congruent to C prime D prime, the angle ADC congruent to the angle A prime D prime C prime. From these congruences and the consideration of the triangles BCD and B prime C prime D prime, it follows by virtue of axiom 4, 6 that the angles CBD and C prime B prime D prime are congruent. As an immediate consequence of Theorem 12, we have a similar theorem concerning the congruence of vertical angles. Theorem 13. That the angle HK of the plane alpha be congruent to the angle H prime K prime of the plane alpha prime, and furthermore, let L be a half-ray in the plane alpha emanating from the vertex of the angle HK and lying within this angle. Then there always exists in the plane alpha prime a half-ray L prime emanating from the vertex of the angle H prime K prime and lying within this angle, so that we have the angle HL congruent to the angle H prime L prime, the angle KL congruent to the angle K prime L prime. Proof: we will represent the vertices of the angles HK and H prime K prime by O and O prime respectively, and so select upon the sides h, k, h prime, k prime, the points a, b, a prime, b prime, that the congruences OA congruent to O prime, A prime, OB congruent to O prime, B prime are fulfilled. Because of the congruence of the triangles OAB and O prime, A prime, B prime, we have at once AB congruent to A prime, B prime, the angle OAB congruent to the angle O prime, A prime, B prime, the angle OBA congruent to the angle O prime, B prime, A prime. Let the straight line AB intersect L in C. Take the point C prime upon the segment A prime, B prime so that A prime, C prime is congruent to AC. Then O prime, C prime is the required half ray. In fact, it follows directly from these congruences by aid of axiom 4,3 that BC is congruent to B prime, C prime. Furthermore, the triangles OAC and O prime, A prime, C prime are congruent to each other, and the same is true also of the triangles OCB and O prime, B prime, C prime. With this, our proposition is demonstrated. In a similar manner, we obtain the following proposition. Theorem 14. Let H, K, L and H prime, K prime, L prime be two sets of three half rays, where those of each set emanate from the same point and lie in the same plane. Then, if the congruences, the angle HL congruent to the angle H prime L prime, the angle KL congruent to the angle K prime L prime are fulfilled, the following congruence is also valid, namely the angle HK congruent to the angle H prime K prime. By aid of theorems 12 and 13, it is possible to deduce the following simple theorem, which Euclid held, although it seems to me wrongly, to be an axiom. Theorem 15. All right angles are congruent to one another. Proof that the angle BAD be congruent to its supplementary angle CAD, and likewise let the angle B prime, A prime, D prime be congruent to its supplementary angle C prime, A prime, D prime. Hence the angles BAD, CAD, B prime, A prime, D prime, and C prime, A prime, D prime are all right angles. We will assume that the contrary of our proposition is true, namely that the right angle B prime, A prime, D prime is not congruent to the right angle BAD, and will show that this assumption leads to a contradiction. We lay off the angle B prime, A prime, D prime upon the half ray AB in such a manner that the side AD double prime arising from this operation falls either within the angle BAD or within the angle CAD. Suppose, for example, the first of these possibilities to be true. Because of the congruence of the angles B prime, A prime, D prime, and BAD double prime, it follows from theorem 12 that angle C prime, A prime, D prime is congruent to angle CAD double prime. And as the angles B prime, A prime, D prime, and C prime, A prime, D prime are congruent to each other, then by 4,5, the angle BAD double prime must be congruent to CAD double prime. Furthermore, since the angle BAD is congruent to the angle CAD, it is possible, by theorem 13, to find within the angle CAD a half-ray AD triple prime emanating from A, so that the angle BAD double prime will be congruent to the angle CAD triple prime, and also the angle DAD double prime will be congruent to the angle DAD triple prime. The angle BAD double prime was shown to be congruent to the angle CAD double prime, and hence, by axiom 4,5, the angle CAD double prime is congruent to the angle CAD triple prime. This, however, is not possible, for according to axiom 4,4, an angle can be laid off in a plane upon a given side of a given half ray in only one way, With this, our proposition is demonstrated. We can now introduce, in accordance with common usage, the terms acute angle and obtuse angle. The theorem relating to the congruence of the base angles A and B of an equilateral triangle ABC follows immediately by the application of axiom 4, 6 to the triangles ABC and BAC. By aid of this theorem, in addition to theorem 14, we can easily demonstrate the following proposition. Theorem 16, third theorem of congruence for triangles. If two triangles have the three sides of one congruent respectively to the corresponding three sides of the other, the triangles are congruent. Any finite number of points is called a figure. If all the points lie in a plane, the figure is called a plane figure. Two figures are said to be congruent if their points can be arranged in a one-to-one correspondence, so that the corresponding segments and the corresponding angles of the two figures are in every case congruent to each other. Congruent figures have, as may be seen from theorems 9 and 12, the following properties. 3 points of a figure lying in a straight line are likewise in a straight line in every figure congruent to it. In congruent figures, the arrangement of the points in corresponding planes with respect to corresponding lines is always the same. The same is true of the sequence of corresponding points situated on corresponding lines. The most general theorems relating to congruences in a plane and in space may be expressed as follows. Theorem 17. If A, B, C, ... and A prime, B prime, C prime, ... are congruent plane figures and P is a point in the plane of the first, then it is always possible to find a point P in the plane of the second figure so that A, B, C, ... P and A prime, B prime, C prime, ... P prime shall likewise be congruent figures. If the two figures have at least 3 points not lying in a straight line, then the selection of P prime can be made in only one way. Theorem 18. If A, B, C, ... and A prime, B prime, C prime, ... are congruent figures and P represents any arbitrary point, then there can always be found a point P prime, so that the two figures A, B, C, ... P and A prime, B prime, C prime, ... P prime shall likewise be congruent. If the figure A, B, C, ... P contains at least 4 points not lying in the same plane, then the determination of P prime can be made in but one way. This theorem contains an important result, namely that all the facts concerning space which have reference to congruence, that is to say, to displacements in space, are, by the addition of the axioms of groups 1 and 2, exclusively the consequence of the 6 linear and plane axioms mentioned above. Hence, it is not necessary to assume the axiom of parallels in order to establish these facts. If we take, in addition to the axioms of congruence, the axiom of parallels, we can then easily establish the following propositions. Theorem 19. If two parallel lines are cut by a third straight line, the alternate interior angles and also the exterior interior angles are congruent. Conversely, if the alternate interior or the exterior interior angles are congruent, the given lines are parallel. Theorem 20. The sum of the angles of a triangle is 2 right angles. Definitions. If M is an arbitrary point in the plane alpha, the totality of all points A, for which the segments MA are congruent to one another, is called a circle. M is called the center of the circle. From this definition can be easily deduced, with the help of the axioms of groups 3 and 4, the known properties of the circle. In particular, the possibility of constructing a circle through any 3 points not lying in a straight line, as also the congruence of all angles inscribed in the same segment of a circle, and the theorem relating to the angles of an inscribed quadrilateral. End of section 7. Chapter 1, Section 8 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 1. The 5 Groups of Axioms. Section 8, Group 5, Axiom of Continuity. Archimedean Axiom. This axiom makes possible the introduction into geometry of the idea of continuity. In order to state this axiom, we must first establish a convention concerning the equality of 2 segments. For this purpose, we can either base our idea of equality upon the axioms relating to the congruence of segments and define as equal the correspondingly congruent segments, or upon the basis of groups 1 and 2, we may determine how, by suitable constructions, see Chapter 5, Section 24, a segment is to be laid off from a point of a given straight line so that a new, definite segment is obtained equal to it. In conformity with such a convention, the axiom of Archimedes may be stated as follows. 5. Let A1 be any point upon a straight line between the arbitrarily chosen points A and B. Take the points A2, A3, A4, ... so that A1 lies between A and A2, A2 between A1 and A3, A3 between A2 and A4, etc. Moreover, let the segments AA1, A1, A2, A2, A3, A3, A4, ... be equal to one another. Then, among this series of points, there always exists a certain point A sub n, such that B lies between A and A sub n. The axiom of Archimedes is a linear axiom. Remark, to the preceding 5 groups of axioms we may add the following one, which, although not of a purely geometrical nature, merits particular attention from a theoretical point of view. It may be expressed in the following form. Axiom of completeness, Vollständigkeit. To a system of points, straight lines, and planes, it is impossible to add other elements in such a manner that the system, thus generalized, shall form a new geometry obeying all of the 5 groups of axioms. In other words, the elements of geometry form a system which is not susceptible of extension if we regard the 5 groups of axioms as valid. This axiom gives us nothing directly concerning the existence of limiting points or of the idea of convergence. Nevertheless, it enables us to demonstrate Bolzano's theorem, by virtue of which, for all sets of points situated upon a straight line between 2 definite points of the same line, there exists necessarily a point of condensation, that is to say, a limiting point. From a theoretical point of view, the value of this axiom is that it leads indirectly to the introduction of limiting points, and hence renders it possible to establish a one-to-one correspondence between the points of a segment and the system of real numbers. However, in what is to follow, no use will be made of the axiom of completeness. End of section 8. Chapter 2, Section 9 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 2, Compatibility and Mutual Independence of the Axioms. Section 9, Compatibility of the Axioms. The axioms, which we have discussed in the previous chapter, and have divided into 5 groups, are not contradictory to one another. That is to say, it is not possible to deduce from these axioms, by any logical process of reasoning, a proposition which is contradictory to any of them. To demonstrate this, it is sufficient to construct a geometry where all of the 5 groups are fulfilled. To this end, let us consider a domain omega, consisting of all those algebraic numbers which may be obtained by beginning with the number 1 and applying to it a finite number of times the 4 arithmetical operations: addition, subtraction, multiplication, and division, and the operation the square root of 1 plus w squared, where w represents a number arising from the 5 operations already given. Let us regard a pair of numbers, x, y, of the domain omega as defining a point, and the ratio of 3 such numbers, u v w, of omega, where u, v are not both equal to 0, as defining a straight line. Furthermore, let the existence of the equation ux plus vy plus w equals 0 express the condition that the point xy lies on the straight line u v w. Then, as one readily sees, axiom 1 through 2, and 3 are fulfilled. The numbers of the domain omega are all real numbers. If now we take into consideration the fact that these numbers may be arranged according to magnitude, we can easily make such necessary conventions concerning our points and straight lines as will also make the axioms of order group 2 hold. In fact, if x1, y1, x2, y2, x3, y3, ... are any points whatever of a straight line, then this may be taken as their sequence on this straight line, providing the numbers x1, x2, x3, ... or the numbers y1, y2, y3, ... either all increase or decrease in the order of the sequence given here. In order that axiom 2, 5 shall be fulfilled, we have merely to assume that all the points corresponding to the values of x and y, which make ux plus vy plus w less than 0 or greater than 0, shall fall respectively upon the one side or upon the other side of the straight line UVW. We can easily convince ourselves that this convention is in accordance with those which precede and by which the sequence of points on a straight line has already been determined. The laying off of segments and of angles follows by the known methods of analytical geometry. A transformation of the form x prime equal x plus a, y prime equal y plus b produces a translation of segments and of angles. Furthermore, if in the accompanying figure we represent the point 0, 0 by O and the point 1, 0 by E, then, corresponding to a rotation of the angle COE about O as a center, any point xy is transformed into another point x prime, y prime, so related that x prime equal a divided by the square root of a squared plus b squared times x, minus b divided by the square root of a squared plus b squared times y. Y prime equal b divided by the square root of a squared plus b squared times x plus a divided by the square root of a squared plus b squared times y. Since the number, the square root of a squared plus b squared equals a times the square root of 1 plus the quantity b divided by a squared belongs to the domain omega, it follows that, under the conventions which we have made, the axioms of congruence, group 4, are fulfilled. The same is true of the axiom of Archimedes. From these considerations, it follows that every contradiction resulting from our system of axioms must also appear in the arithmetic related to the domain omega. The corresponding considerations for the geometry of space present no difficulties. If, in the preceding development, we had selected the domain of all real numbers instead of the domain omega, we should have obtained likewise a geometry in which all of the axioms of groups 1 through 5 are valid. For the purposes of our demonstrations, however, it was sufficient to take the domain omega containing on an innumerable set of elements. End of section 9. Chapter 2, Section 10 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 2, Compatibility and Mutual Independence of the Axioms. Section 10, Independence of the Axioms of Parallels, Non-euclidean Geometry. Having shown that the axioms of the above system are not contradictory to one another, it is of interest to investigate the question of their mutual independence. In fact, it may be shown that none of them can be deduced from the remaining ones by any logical process of reasoning. First of all, so far as the particular axioms of groups 1, 2, and 4 are concerned, it is easy to show that the axioms of these groups are each independent of the other of the same group. According to our presentation, the axioms of groups 1 and 2 form the basis of the remaining axioms. It is sufficient, therefore, to show that each of the groups 2, 4, and 5 is independent of the others. The first statement of the axiom of parallels can be demonstrated by aid of the axioms of groups 1, 2, and 4. In order to do this, join the given point A with any arbitrary point B of the straight line A. Let C be any other point of the given straight line. At the point A on AB, construct the angle ABC so that it shall lie in the same plane alpha as the point C, but upon the opposite side of AB from it. The straight line thus obtained through A does not meet the given straight line A, for if it should cut it, say in the point D, and if we suppose B to be situated between C and D, we could then find on A point D prime, so situated that B would lie between D and D prime, and, moreover, so that we should have AD congruent to BD prime. Because of the congruence of the two triangles ABD and BAD prime, we have also the angle ABD congruent to the angle BAD prime. And since the angles ABD' and ABD are supplementary, it follows from Theorem 12 that the angles BAD and BAD' are also supplementary. This, however, cannot be true, as by Theorem 1, two straight lines cannot intersect in more than one point, which would be the case if BAD and BAD' were supplementary. The second statement of the axiom of parallels is independent of all the other axioms. This may be most easily shown in the following well-known manner. As the individual elements of a geometry of space, select the points, straight lines, and planes of ordinary geometry as constructed in section 9, and regard these elements as restricted in extent to the interior of a fixed sphere. Then, define the congruences of this geometry by aid of such linear transformations of the ordinary geometry as transform the fixed sphere into itself. By suitable conventions, we can make this non-Euclidean geometry obey all the axioms of our system except the axiom of Euclid, group 3. Since the possibility of the ordinary geometry has already been established, that of the non-Euclidean geometry is now an immediate consequence of the above considerations. End of section 10. Chapter 2, Section 11, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 2, Compatibility and Mutual Independence of the Axioms. Section 11, Independence of the Axioms of Congruence. We shall show the independence of the axioms of congruence by demonstrating that axiom 4,6, or what amounts to the same thing, that the first theorem of congruence for triangles, theorem 10, cannot be deduced from the remaining axioms 1, 2, 3, 4, 1 through 5, 5, by any logical process of reasoning. Select as the points, straight lines, and planes of our new geometry of space, the points, straight lines, and planes of ordinary geometry, and define the laying off of an angle as in ordinary geometry, for example, as explained in section 9. We will, however, define the laying off of segments in another manner. Let A1, A2 be two points which, in ordinary geometry, have the coordinates x1, y1, z1, and x2, y2, z2, respectively. We will now define the length of the segment A1, A2 as the positive value of the expression, the square root of the quantity x1 minus x2 plus y1 minus y2 squared plus the quantity y1 minus y2 squared plus the quantity z1 minus z2 squared, and call the two segments A1, A2 and A1', A2' congruent when they have equal lengths in the sense just defined. It is at once evident that, in the geometry of space thus defined, the axioms 1, 2, 3, 4, 1 through 2, 4 through 5, 5 are all fulfilled. In order to show that axiom 4,3 also holds, we select an arbitrary straight line A and upon it 3 points, A1, A2, A3, so that A2 shall lie between A1 and A3. Let the points x, y, z of the straight line A be given by means of the equations x equal lambda t plus lambda prime, y equal mu t plus mu prime, z equal nu t plus nu prime, where lambda, lambda prime, mu, mu prime, nu, nu prime represent certain constants and t is a parameter. If t1, t2 less than t1, t3 less than t2 are the values of the parameter corresponding to the points a1, a2, a3, we have as the lengths of the three segments a1, a2, a2, a3, and a1, a3 respectively the following values. The quantity t1 minus t2 times the absolute value of the square root of the quantity lambda plus mu squared plus mu squared plus nu squared. The quantity t2 minus t3 times the absolute value of the square root of the quantity lambda plus mu squared plus mu squared plus nu squared. The quantity t1 minus t3 times the absolute value of the square root of the quantity lambda plus mu squared plus mu squared plus nu squared. Consequently, the length of a1, a3 is equal to the sum of the lengths of the segments a1, a2, and a2, a3. But this result is equivalent to the existence of axiom 4, 3. Axiom 4, 6, or rather the first theorem of congruence for triangles, is not always fulfilled in this geometry. Consider, for example, in the plane z equals 0, the 4 points O having the coordinates x equals 0, y equals 0. A having the coordinates x equal 1, y equals 0. B having the coordinates x equals 0, y equal 1. C having the coordinates x equal 1/2, y equal 1/2. Then, in the right triangles, OAC and OBC, the angles at C, as also the adjacent sides AC and BC, are respectively congruent. For the side OC is common to the two triangles, and the sides AC and BC have the same length, namely 1/2. However, the third sides OA and OB have the lengths 1 and square root of 2, respectively, and are not therefore congruent. It is not difficult to find in this geometry two triangles for which axiom 4, 6 itself is not valid. End of section 11. Chapter 2, Section 12 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 2, Compatibility and Mutual Independence of the Axioms. Section 12, Independence of the Axiom of Continuity, Non-archimedean Geometry. In order to demonstrate the independence of the axiom of Archimedes, we must produce a geometry in which all of the axioms are fulfilled, with the exception of the one in question. For this purpose, we construct a domain omega of t of all those algebraic functions of t which may be obtained from t by means of the 4 arithmetical operations of addition, subtraction, multiplication, division, and the 5th operation, the square root of 1 plus w squared, where w represents any function arising from the application of these 5 operations. The elements of omega t, just as was previously the case for omega, constitute an enumerable set. These 5 operations may all be performed without introducing imaginaries, and that in only one way. The domain omega t contains, therefore, only real single-valued functions of t. Let C be any function of the domain omega of t. Since this function C is an algebraic function of t, it can in no case vanish for more than a finite number of values of t, and hence for sufficiently large positive values of t, it must remain always positive or always negative. Let us now regard the functions of the domain omega of t as a kind of complex numbers. In the system of complex numbers thus defined, all of the ordinary rules of operation evidently hold. Moreover, if a, b are any two distinct numbers of this system, then a is said to be greater than or less than b, written a greater than b or a less than b, according as the difference c equal a minus b is always positive or always negative for sufficiently large values of t. By the adoption of this convention for the numbers of our system, it is possible to arrange them according to their magnitude in a manner analogous to that employed for real numbers. We readily see also that, for this system of complex numbers, the validity of an inequality is not destroyed by adding the same or equal numbers to both members, or by multiplying both members by the same number, providing it is greater than 0. If n is any arbitrary positive integral rational number, then, for the two numbers n and t of the domain omega of t, the inequality n less than t certainly holds, for the difference n minus t, considered as a function of t, is always negative for sufficiently large values of t. We express this fact in the following manner. The two numbers L and T of the domain omega of t, each of which is greater than 0, possess the property that any multiple whatever of the first always remains smaller than the second. From the complex numbers of the domain omega of t, we now proceed to construct a geometry in exactly the same manner as in section 9, where we took as the basis of our consideration the algebraic numbers of the domain omega. We will regard a system of three numbers x, y, z of the domain omega of t as defining a point, and the ratio of any four such numbers, u, v, w, r, where u, v, w are not all 0, as defining a plane. Finally, the existence of the equation xu plus yv plus zw plus r equals 0 shall express the condition that the point x, y, z lies in the plane u, v, w, r. Let the straight line be defined in our geometry as the totality of all the points lying simultaneously in the same two planes. If now we adopt conventions corresponding to those of section 9, concerning the arrangement of elements and the laying off of angles and of segments, we shall obtain a non-archimedean geometry where, as the properties of the complex number system already investigated show, all of the axioms, with the exception of that of Archimedes, are fulfilled. In fact, we can lay off successively the segment 1 upon the segment t an arbitrary number of times without reaching the endpoint of the segment t, which is a contradiction to the axiom of Archimedes. End of section 12. Chapter 3, Section 13 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 3, The theory of proportion. Section 13. Complex number systems. At the beginning of this chapter, we shall present briefly certain preliminary ideas concerning complex number systems, which will later be of service to us in our discussion. The real numbers form, in their totality, a system of things having the following properties. Theorems of connection 1 through 12. 1. From the number a and the number b, there is obtained by addition a definite number c, which we express by writing a plus b equals c, or c equals a plus b. 2. There exists a definite number, which we call 0, such that for every number a, we have a plus 0 equals a, and 0 plus a equals a. 3. If a and b are two given numbers, there exists one and only one number x, and also one and only one number y, such that we have respectively a plus x equals b, y plus a equals b. 4. From the number a and the number b, there may be obtained in another way, namely by multiplication, a definite number c, which we express by writing ab equals c, or c equals ab. 5. There exists a definite number called 1, such that for every number a, we have a times 1 equals a, and 1 times a equals a. 6. If a and b are any arbitrarily given numbers where a is different from 0, then there exists one and only one number x, and also one and only one number y, such that we have, respectively, ax equals b, ya equals b. If a, b, c are arbitrary numbers, the following laws of operation always hold. 7. A plus the quantity b plus c equals the quantity a plus b plus c. 8. A plus b equals b plus a. 9. A times the quantity bc equals the quantity ab times c. 10. A times the quantity b plus c equals ab plus ac. 11. The quantity a plus b times c equals ac plus bc. 12. ab equals ba. Theorems of order 13 through 16. 13. If a, b are any two distinct numbers, one of these, say a, is always greater than the other. The other number is said to be the smaller of the two. We express this relation by writing a greater than b and b less than a. 14. If a greater than b and b greater than c, then is also a greater than c. 15. If a greater than b, then is also a plus c greater than b plus c, and c plus a greater than c plus b. 16. If a greater than b and c greater than 0, then is also ac greater than bc and ca greater than cb. Theorem of Archimedes 17. 17. If a, b are any two arbitrary numbers such that a greater than 0 and b greater than 0, it is always possible to add a to itself a sufficient number of times so that the resulting sum shall have the property that a plus a plus a plus ... plus a greater than b. A system of things possessing only a portion of the above properties, 1 through 17, is called a complex number system, or simply a number system. A number system is called Archimedean or non-Archimedean according as it does or does not satisfy condition 17. Not every one of the properties 1 through 17 given above is independent of the others. The problem arises to investigate the logical dependence of these properties. Because of their great importance in geometry, we shall, in sections 32, 33, pages 65 through 68, answer 2 definite questions of this character. We will here merely call attention to the fact that, in any case, the last of these conditions, 17, is not a consequence of the remaining properties since, for example, the complex number system, omega of t, considered in section 12, possesses all of the properties 1 through 16, but does not fulfill the laws stated in 17. End of section 13. Chapter 3, Section 14, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 3, The Theory of Proportion. Section 14, Demonstration of Pascal's Theorem. In this and the following chapter, we shall take as the basis of our discussion all of the plane axioms, with the exception of the axiom of Archimedes. That is to say, the axioms 1, 1 through 2 and 2 through 4. In the present chapter, we propose, by aid of these axioms, to establish Euclid's theory of proportion. That is, we shall establish it for the plane, and that independently of the axiom of Archimedes. For this purpose, we shall first demonstrate a proposition which is a special case of the well-known theorem of Pascal, usually considered in the theory of conic sections, and which we shall hereafter, for the sake of brevity, refer to simply as Pascal's theorem. This theorem may be stated as follows. Theorem 21, Pascal's theorem. Given the two sets of points, A, B, C, and A', B', C', so situated respectively upon two intersecting straight lines, that none of them fall at the intersection of these lines. If CB' is parallel to BC', and CA' is also parallel to AC', then BA' is parallel to AB'. In order to demonstrate this theorem, we shall first introduce the following notation. In a right triangle, the base A is uniquely determined by the hypotenuse C and the base angle alpha, included by A and C. We shall express this fact briefly by writing A equal alpha C. Hence, the symbol alpha C always represents a definite segment, providing C is any given segment whatever, and alpha is any given acute angle. Furthermore, if C is any arbitrary segment, and alpha, beta are any two acute angles whatever, then the two segments alpha beta C and beta alpha C are always congruent. That is, we have alpha beta C equals beta alpha C, and consequently, the symbols alpha and beta are interchangeable. In order to prove this statement, we take the segment C equal AB, and with A as a vertex, lay off upon the one side of this segment the angle alpha, and upon the other the angle beta. Then, from the point B, let fall upon the opposite sides of the alpha and beta the perpendiculars BC and BD respectively. Finally, join C with D, and let fall from A the perpendicular AE upon CD. Since the two angles ACB and ADB are right angles, the 4 points ABCD are situated upon a circle. Consequently, the angles ACD and ABD, being inscribed in the same segment of the circle, are congruent. But the angles ACD and CAE, taken together, make a right angle, and the same is true of the two angles ABD and BAD. Hence, the two angles CAE and BAD are also congruent. That is to say, the angle CAE congruent to beta, and therefore the angle DAE congruent to alpha. From these considerations, we have immediately the following congruences of segments: beta C congruent to AD, alpha C congruent to AC, alpha beta C congruent to alpha AD congruent to AE, beta alpha C congruent to beta AC congruent to AE. From these, the validity of the congruence in question follows. Returning now to the figure in connection with Pascal's theorem, denote the intersection of the two given straight lines by O, and the segments OA, OB, OC, OA prime, OB prime, OC prime, CB prime, BC prime, CA prime, AC prime, BA prime, AB prime, by A, B, C, A prime, B prime, C prime, L, L star, M, M star, N, N star, respectively. Let fall from the point O a perpendicular upon each of the segments L, M, N. The perpendicular to L will form with the straight lines OA and OA prime acute angles, which we shall denote by lambda prime and lambda respectively. Likewise, the perpendiculars to M and N form with these same lines OA and OA prime acute angles, which we shall denote by mu prime mu and nu prime nu respectively. If we now express, as indicated above, each of these perpendiculars in terms of the hypotenuse and base angle, we have the three following congruences of segments. Equation 1. Lambda b prime congruent to lambda prime c. Equation 2. Mu a prime congruent to mu prime c. Equation 3. Nu a prime congruent to nu prime b. But since, according to our hypothesis, L is parallel to L star, and M is parallel to M star, the perpendiculars from O falling upon L star and M star must coincide with the perpendiculars from the same point falling upon L and M, and consequently we have Equation 4. Lambda c prime congruent to lambda prime b. Equation 5. Mu c prime congruent to mu prime a. Multiplying both members of congruence, equation 3, by the symbol lambda prime mu, and remembering that, as we have already seen, the symbols in question are commutative, we have nu lambda prime mu a prime congruent to nu prime mu lambda prime b. In this congruence, we may replace mu a prime in the first member by its value given in equation 2, and lambda prime b in the second member by its value given in equation 4. thus obtaining as a result nu lambda prime mu prime c congruent to nu prime mu lambda c prime, or nu mu prime lambda prime c congruent to nu prime lambda mu c prime. Here again in this congruence we can, by aid of equation 1, replace lambda prime c by lambda b prime, and by aid of equation 5 we may replace in the second member mu c prime by mu prime a. We then have nu mu prime lambda b prime congruent to nu prime lambda mu prime a, or lambda mu prime nu b prime congruent to lambda mu prime nu prime a. Because of the significance of our symbols, we can conclude at once from this congruence that mu prime nu b prime congruent to mu prime nu prime a, and consequently that equation 6 nu b prime congruent to nu prime a. If now we consider the perpendicular let fall from O upon n and draw perpendiculars to this same line from the points A and B prime, then congruence, equation 6, shows that the feet of the last two perpendiculars must coincide. That is to say, the straight line n star equal AB prime makes a right angle with the perpendicular to n, and consequently is parallel to n. This establishes the truth of Pascal's theorem. Having given any straight line whatever, together with an arbitrary angle and a point lying outside of the given line, we can, by constructing the given angle and drawing a parallel line, find a straight line passing through the given point and cutting the given straight line at the given angle. By means of this construction, we can demonstrate Pascal's theorem in the following very simple manner, for which, however, I am indebted to another source. Through the point B, draw a straight line cutting OA prime in the point D prime, and making with it the angle OCA prime, so that the congruence, equation 1 star, the angle OCA prime congruent to the angle OD prime B is fulfilled. Now, according to a well-known property of circles, CBD prime A prime is an inscribed quadrilateral, and consequently, by aid of the theorem concerning the congruence of angles inscribed in the same segment of a circle, we have the congruence, equation 2 star, the angle OBA prime congruent to the angle OD prime C. Since, by hypothesis, CA prime and AC prime are parallel, we have equation 3 star, the angle OCA prime congruent to the angle OAC prime. And from equation 1 star and equation 3 star, we obtain the congruence, the angle OD prime B congruent to the angle OAC prime. However, BAD prime C prime is also an inscribed quadrilateral, and consequently, by virtue of the theorem relating to the angles of such a quadrilateral, we have the congruence, equation 4 star, the angle OAD prime congruent to the angle OC prime B. But as CB prime is, by hypothesis, parallel to BC prime, we have also equation 5 star, the angle OB prime C congruent to the angle OC prime B. From equation 4 star and equation 5 star, we obtain the congruence, the angle OAD prime congruent to the angle OB prime C, which shows that CAD'(B' is also an inscribed quadrilateral, and hence the congruence, equation 6 star, the angle OAB' congruent to the angle OD'(C) is valid. From equation 2 star and equation 6 star, it follows that the angle OBA' congruent to the angle OAB', and this congruence shows that BA' and AB' are parallel, as Pascal's theorem demands. In case D' coincides with one of the points, A', B', C', it is necessary to make a modification of this method, which evidently is not difficult to do. End of section 14. Chapter 3, Section 15 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 3, The Theory of Proportion. Section 15, An Algebra of Segments based upon Pascal's theorem. Pascal's theorem, which was demonstrated in the last section, puts us in a position to introduce into geometry a method of calculating with segments, in which all of the rules for calculating with real numbers remain valid without any modification. Instead of the word congruent and the sign congruent, we make use, in the algebra of segments, of the word equal and the sign equals. If A, B, C are 3 points of a straight line, and if B lies between A and C, then we say that C equal AC is the sum of the two segments, A equal AB and B equal BC. We indicate this by writing C equals A plus B. The segments A and B are said to be smaller than C, which fact we indicate by writing A less than C, B less than C. On the other hand, C is said to be larger than A and B, and we indicate this by writing C greater than A, C greater than B. From the linear axioms of congruence, axioms 4, 1 through 3, we easily see that, for the above definition of addition of segments, the associative law, A plus the quantity B plus C equals the quantity A plus B plus C, as well as the commutative law, A plus B equals B plus A, is valid. In order to define geometrically the product of two segments A and B, we shall make use of the following construction. Select any convenient segment which, having been selected, shall remain constant throughout the discussion, and denote the same by 1. Upon the one side of a right angle, lay off from the vertex O the segment 1 and also the segment B. Then, from O, lay off upon the other side of the right angle the segment A. Join the extremities of the segments 1 and A by a straight line, and from the extremity of B, draw a line parallel to this straight line. This parallel will cut off from the other side of the right angle a segment C. We call this segment C the product of the segments A and B, and indicate this relation by writing C equals AB. We shall now demonstrate that, for this definition of the multiplication of segments, the commutative law AB equals BA holds. For this purpose, we construct in the above manner the product AB. Furthermore, lay off from O upon the first side 1 of the right angle, the segment A, and upon the other side 2, the segment B. Connect by a straight line the extremity of the segment 1 with the extremity of B situated on 2, and draw through the endpoint of A on 1 a line parallel to this straight line. This parallel will determine by its intersection with the side 2 the segment BA. But because the two dotted lines are, by Pascal's theorem, parallel, the segment BA just found coincides with the segment AB previously constructed, and our proposition is established. In order to show that the associative law A times the quantity BC equals the quantity AB times C holds for the multiplication of segments, we construct first of all the segment D equals BE, then DA, after that the segment E equals BA, and finally EC. By virtue of Pascal's theorem, the extremities of the segments DA and EC coincide, as may be clearly seen from Figure 24. If now we apply the commutative law which we have just demonstrated, we obtain the above formula, which expresses the associative law for the multiplication of two segments. Finally, the distributive law A times the quantity B plus C equals AB plus AC also holds for our algebra of segments. In order to demonstrate this, we construct the segments AB, AC, and A times the quantity B plus C, and draw through the extremity of the segment C, Figure 25, a straight line parallel to the other side of the right angle. From the congruence of the two right-angled triangles, which are shaded in the figure, and the application of the theorem relating to the equality of the opposite sides of a parallelogram, the desired result follows. If B and C are any two arbitrary segments, there is always a segment A to be found such that C is equal to AB. This segment A is denoted by C over B and is called the quotient of C by B. End of section 15. Chapter 3, Section 16 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 3, The Theory of Proportion. Section 16, Proportion and the Theorems of Similitude. By aid of the preceding algebra of segments, we can establish Euclid's theory of proportion in a manner free from objections and without making use of the axiom of Archimedes. If A, B, A', B' are any four segments whatever, the proportion A is to B as A' is to B' expresses nothing else than the validity of the equation A B' equals B A'. Definition: two triangles are called similar when the corresponding angles are congruent. Theorem 22. If A, B, and A', B' are homologous sides of two similar triangles, we have the proportion A is to B as A' is to B'. Proof: we shall first consider the special case where the angle included between A and B and the one included between A' and B' are right angles. Moreover, we shall assume that the two triangles are laid off in one and the same right angle. Upon one of the sides of this right angle, we lay off from the vertex O the segment 1, and through the extremity of this segment, we draw a straight line parallel to the hypotenuses of the two triangles. This parallel determines upon the other side of the right angle a segment E. Then, according to our definition of the product of two segments, we have B equal EA, B prime equal EA prime, from which we obtain AB prime equal BA prime. That is to say, A is to B as A prime is to B prime. Let us now return to the general case. In each of the two similar triangles, find the point of intersection of the bisectors of the three angles. Denote these points by S and S prime. From these points, let fall upon the sides of the triangles the perpendiculars R and R prime, respectively. Denote the segments thus determined upon the sides of the triangles by A sub B, A sub C, B sub C, B sub A, C sub A, C sub B, and A prime sub B, A prime sub C, B prime sub C, B prime sub A, C prime sub A, C prime sub B, respectively. The special case of our proposition, demonstrated above, gives us then the following proportions. A sub B is to R as A prime sub B is to R prime. B sub C is to R as B prime sub C is to R prime. A sub C is to R as A prime sub C is to R prime. B sub A is to R as B prime sub A is to R prime. By aid of the distributive law, we obtain from these proportions the following. A is to R as A prime is to R prime. B is to R as B prime is to R prime. Consequently, by virtue of the commutative law of multiplication, we have A is to B as A prime is to B prime. From the theorem just demonstrated, we can easily deduce the fundamental theorem in the theory of proportion. This theorem may be stated as follows. Theorem 23. If two parallel lines cut from the sides of an arbitrary angle the segments A, B, and A prime, B prime, respectively, then we have always the proportion A is to B as A prime is to B prime. Conversely, if the four segments A, B, A prime, B prime fulfill this proportion, and if A, A prime, and B, B prime are laid off upon the two sides respectively of an arbitrary angle, then the straight lines joining the extremities of A and B and of A prime and B prime are parallel to each other. End of section 16. Chapter 3, Section 17 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 3. The Theory of Proportion. Section 17. Equations of straight lines and of planes. To the system of segments already discussed, let us now add a second system. We will distinguish the segments of the new system from those of the former one by means of a special sign, and we will call them negative segments in contradistinction to the positive segments already considered. If we introduce also the segment O, which is determined by a single point, and make other appropriate conventions, then all of the rules deduced in section 13 for calculating with real numbers will hold equally well here for calculating with segments. We call special attention to the following particular propositions. We have always a times 1 equals 1 times a equals a. If a times b equals 0, then either a equals 0 or b equals 0. If a is greater than b and c is greater than 0, then AC is greater than BC. In a plane alpha, we now take two straight lines cutting each other in O at right angles as the fixed axes of rectangular coordinates, and lay off from O upon these two straight lines the arbitrary segments x and y. We lay off these segments upon the one side or upon the other side of O, according as they are positive or negative. At the extremities of x and y, erect perpendiculars and determine the point P of their intersection. The segments x and y are called the coordinates of P. Every point of the plane alpha is uniquely determined by its coordinates x, y, which may be positive, negative, or 0. Let L be a straight line in the plane alpha such that it passes through O and also through a point C having the coordinates a, b. If x, y are the coordinates of any point on L, it follows at once from Theorem 22 that a is to b as x is to y, or bx minus ay equals 0 is the equation of the straight line L. If L' is a straight line parallel to L, and cutting off from the x-axis the segment C, then we may obtain the equation of the straight line L' by replacing in the equation for L the segment x by the segment x minus c. The desired equation will then be of the form bx minus ay minus bc equals 0. From these considerations, we may easily conclude, independently of the axiom of Archimedes, that every straight line in a plane is represented by an equation which is linear in the coordinates x, y, and conversely, every such linear equation represents a straight line when the coordinates are segments appertaining to the geometry in question. The corresponding results for the geometry of space may be easily deduced. The remaining parts of geometry may now be developed by the usual methods of analytic geometry. So far in this chapter, we have made absolutely no use of the axiom of Archimedes. If now we assume the validity of this axiom, we can arrange a definite correspondence between the points on any straight line in space and the real numbers. This may be accomplished in the following manner. We first select on a straight line any 2 points, and assign to these points the numbers 0 and 1. Then bisect the segment 0, 1 thus determined, and denote the middle point by the number 1/2. In the same way, we denote the middle of 0, 1/2 by 1/4, etc. After applying this process n times, we obtain a point which corresponds to 1 divided by 2 to the nth power. Now, lay off m times in both directions from the point O the segment O, 1 divided by 2 to the nth power. We obtain in this manner a point corresponding to the numbers m divided by 2 to the nth power and negative m divided by 2 to the nth power. From the axiom of Archimedes, we now easily see that, upon the basis of this association, to each arbitrary point of a straight line there corresponds a single, definite, real number, and indeed such that this correspondence possesses the following property. If A, B, C are any 3 points on a straight line, and alpha, beta, gamma are the corresponding real numbers, and if B lies between A and C, then one of the inequalities, alpha less than beta less than gamma, or alpha greater than beta greater than gamma, is always fulfilled. From the development given in section 9, page 15, it is evident that to every number belonging to the field of algebraic numbers omega, there must exist a corresponding point upon the straight line. Whether to every real number there corresponds a point cannot, in general, be established, but depends upon the geometry to which we have reference. However, it is always possible to generalize the original system of points, straight lines, and planes by the addition of ideal or irrational elements, so that upon any straight line of the corresponding geometry, a point corresponds, without exception, to every system of 3 real numbers. By the adoption of suitable conventions, it may also be seen that, in this generalized geometry, all of the axioms 1 through 5 are valid. This geometry, generalized by the addition of irrational elements, is nothing else than the ordinary analytic geometry of space. End of section 17. Chapter 4, Section 18, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 4, The Theory of Plane Areas. Section 18, Equal Area and Equal Content of Polygons. We shall base the investigations of the present chapter upon the same axioms as were made use of in the last chapter, sections 13 through 17, namely, upon the plane axioms of all the groups, with the single exception of the axiom of Archimedes. This involves then the axioms 1, 1 through 2, and 2 through 4. The theory of proportion as developed in sections 13 through 17, together with the algebra of segments introduced in the same chapter, puts us now in a position to establish Euclid's theory of areas by means of the axioms already mentioned, that is to say, for the plane geometry, and that independently of the axiom of Archimedes. Since, by the development given in the last chapter, pages 23 through 35, the theory of proportion was made to depend essentially upon Pascal's theorem, Theorem 21, the same may then be said here of the theory of areas. This manner of establishing the theory of areas seems to me a very remarkable application of Pascal's theorem to elementary geometry. If we join 2 points of a polygon, P, by any arbitrary broken line lying entirely within the polygon, we shall obtain 2 new polygons, P1 and P2, whose interior points all lie within P. We say that P is decomposed into P1 and P2, or that the polygon P is composed of P1 and P2. Definition: 2 polygons are said to be of equal area when they can be decomposed into a finite number of triangles which are respectively congruent to one another in pairs. Definition: 2 polygons are said to be of equal content when it is possible, by the addition of other polygons having equal area, to obtain two resulting polygons having equal area. From these definitions, it follows at once that by combining polygons having equal area, we obtain, as a result, polygons having equal area. However, if from polygons having equal area, we take polygons having equal area, we obtain polygons which are of equal content. Furthermore, we have the following propositions. Theorem 24. If each of two polygons, P1 and P2, is of equal area to a third polygon, P3, then P1 and P2 are themselves of equal area. If each of two polygons is of equal content to a third, then they are themselves of equal content. Proof. By hypothesis, we can so decompose each of the polygons P1 and P2 into such a system of triangles that any triangle of either of these systems will be congruent to the corresponding triangle of a system into which P3 may be decomposed. If we consider simultaneously the two decompositions of P3, we see that, in general, each triangle of one decomposition is broken up into polygons by the segments which belong to the other decomposition. Let us add to these segments a sufficient number of others to reduce each of these polygons to triangles, and apply the two resulting methods of decompositions to P1 and P2, thus breaking them up into corresponding triangles. Then, evidently, the two polygons, P1 and P2, are each decomposed into the same number of triangles, which are respectively congruent by pairs. Consequently, the two polygons are, by definition, of equal area. The proof of the second part of the theorem follows without difficulty. We define in the usual manner the terms rectangle, base, and height of a parallelogram, base and height of a triangle. End of section 18. Chapter 4, Section 19 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 4, The Theory of Plane Areas. Section 19, Parallelograms and Triangles having equal bases and equal altitudes. The well-known reasoning of Euclid, illustrated by the accompanying figure, furnishes a proof for the following theorem. Theorem 25. Two parallelograms having equal bases and equal altitudes are also of equal content. We have also the following well-known proposition. Theorem 26. Any triangle ABC is always of equal area to a certain parallelogram having an equal base and an altitude half as great as that of the triangle. Proof. Bisect AC in D and BC in E and extend the line DE to F, making EF equal to DE. Then the triangles DEC and FBE are congruent to each other, and consequently the triangle ABC and the parallelogram ABFD are of equal area. From theorems 25 and 26, we have at once, by aid of theorem 24, the following proposition. Theorem 27. Two triangles having equal bases and equal altitudes have also equal content. It is usual to show that two triangles having equal bases and equal altitudes are always of equal area. It is to be remarked, however, that this demonstration cannot be made without the aid of the axiom of Archimedes. In fact, we may easily construct in our non-archimedean geometry, see section 12, page 21, two triangles so that they shall have equal bases and equal altitudes, and, consequently, by theorem 27, must be of equal content, but which are not, however, of equal area. As such an example, we may take the two triangles ABC and ABD having each the base AB equal 1, and the altitude 1, where the vertex of the first triangle is situated perpendicularly above A, and in the second triangle, the foot F of the perpendicular let fall from the vertex D upon the base is so situated that AF equals T. The remaining propositions of elementary geometry concerning the equal content of polygons, and in particular the Pythagorean theorem, are all simple consequences of the theorems which we have already given. In the further development of the theory of area, we meet, however, with an essential difficulty. In fact, the discussion so far leaves it still in doubt whether all polygons are not, perhaps, of equal content. In this case, all of the propositions which we have given would be devoid of meaning and hence of no value. Furthermore, the more general question also arises as to whether two rectangles of equal content and having one side in common do not also have their other sides congruent. That is to say, whether a rectangle is not definitely determined by means of a side and its area. As a closer investigation shows, in order to answer this question, we need to make use of the converse of theorem 27. This may be stated as follows. Theorem 28. If two triangles have equal content and equal bases, they have also equal altitudes. This fundamental theorem is to be found in the first book of Euclid's Elements as Proposition 39. In the demonstration of this theorem, however, Euclid appeals to the general proposition relating to magnitudes. Ketolu tumarus misonestin. A method of procedure which amounts to the same thing as introducing a new geometrical axiom concerning areas. It is now possible to establish the above theorem, and hence the theory of areas, in the manner we have proposed, that is to say, with the help of the plane axioms, and without making use of the axiom of Archimedes. In order to show this, it is necessary to introduce the idea of the measure of area. End of section 19. Chapter 4, Section 20, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 4, The Theory of Plane Areas. Section 20, The Measure of Area of Triangles and Polygons. Definition: if in a triangle ABC having the sides ABC, we construct the two altitudes h sub A equal AD, h sub B equal BE, then, according to Theorem 22, it follows from the similarity of the triangles BCE and ACD that we have the proportion A is to h sub B as B is to h sub A. That is, we have A times h sub A equals B times h sub B. This shows that the product of the base and the corresponding altitude of a triangle is the same whichever side is selected as the base. The half of this product of the base and the altitude of a triangle, delta, is called the measure of area of the triangle, delta, and we denote it by f of delta. A segment joining a vertex of a triangle with a point of the opposite side is called a transversal. A transversal divides the given triangle into two others, having the same altitude and having bases which lie in the same straight line. Such a decomposition is called a transversal decomposition of the triangle. Theorem 29. If a triangle delta is decomposed by means of arbitrary straight lines into a finite number of triangles, delta sub k, then the measure of area of delta is equal to the sum of the measures of area of the separate triangles, delta sub k. Proof: from the distributive law of our algebra of segments, it follows immediately that the measure of area of an arbitrary triangle is equal to the sum of the measures of area of two such triangles as arise from any transversal decomposition of the given triangle. The repeated application of this proposition shows that the measure of area of any triangle is equal to the sum of the measures of area of all the triangles arising by applying the transversal decomposition an arbitrary number of times in succession. In order to establish the corresponding proof for an arbitrary decomposition of the triangle delta into the triangles delta sub k, draw from the vertex A of the given triangle delta a transversal through each of the points of division of the required decomposition. That is to say, draw a transversal through each vertex of the triangles delta sub k. By means of these transversals, the given triangle delta is decomposed into certain triangles delta sub t. Each of these triangles delta sub t is broken up by the segments which determine this decomposition into certain triangles and quadrilaterals. If now, in each of the quadrilaterals, we draw a diagonal, then each triangle delta sub t is decomposed into certain other triangles delta sub ts. We shall now show that the decomposition into the triangles delta sub ts is for the triangles delta sub t as well as for the triangles delta sub k, nothing else than a series of transversal decompositions. In fact, it is at once evident that any decomposition of a triangle into partial triangles may always be affected by a series of transversal decompositions, providing in this decomposition points of division do not exist within the triangle, and further, that at least one side of the triangle remains free from points of division. We easily see that these conditions hold for the triangles delta sub t. In fact, the interior of each of these triangles has also one side, namely the side opposite the point A, contains no points of division. Likewise, for each of the triangles delta sub k, the decomposition into delta sub ts is reducible to transversal decompositions. Let us consider a triangle, delta sub k. Among the transversals of the triangle delta emanating from the point A, there is always a definite one to be found, which either coincides with a side of delta sub k, or which itself divides delta sub k into two triangles. In the first case, the side in question always remains free from further points of division by the decomposition into the triangles delta sub ts. In the second case, the segment of the transversal contained within the triangle delta sub k is a side of the two triangles arising from the division, and this side certainly remains free from further points of division. According to the considerations set forth at the beginning of this demonstration, the measure of area f of delta of the triangle delta is equal to the sum of the measures of area f of delta sub t of all the triangles delta sub t, and this sum is in turn equal to the sum of all the measures of area f of delta sub ts. However, the sum of the measures of area f of delta sub k of all the triangles delta sub k is also equal to the sum of the measures of area f of delta sub ts. Consequently, we have finally that the measure of area f of delta is also equal to the sum of all the measures of area f of delta sub k. And with this conclusion, our demonstration is completed. Definition: if we define the measure of area f of p of a polygon as the sum of the measures of area of all the triangles into which the polygon is, by a definite decomposition, divided, then upon the basis of Theorem 29, and by a process of reasoning similar to that which we have employed in 18 to prove Theorem 24, we know that the measure of area of a polygon is independent of the manner of decomposition into triangles, and consequently is definitely determined by the polygon itself. From this we obtain, by aid of Theorem 29, the result that polygons of equal area have also equal measures of area. Furthermore, if P and Q are two polygons of equal content, then there must exist, according to the above definition, two other polygons P' and Q' of equal area, such that the polygon composed of P and P' shall be of equal area with the polygon formed by combining the polygons Q and Q'. From the two equations, f of P plus P' equals f of Q plus Q', f of P' equals f of Q', we easily deduce the equation f of P equals f of Q. That is to say, polygons of equal content have also equal measure of area. From this last statement, we obtain immediately the proof of Theorem 28. If we denote the equal bases of the two triangles by G, and the corresponding altitudes by h and h' respectively, then we may conclude from the assumed equality of content of the two triangles that they must also have equal measures of area. That is to say, it follows that 1/2 GH equals 1/2 GH', and consequently, dividing by 1/2 G, we get h equal h', which is the statement made in Theorem 28. End of section 20. Chapter 4, Section 21 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 4, The Theory of Plane Areas. Section 21, Equality of Content and the Measure of Area. In Section 20, we have found that polygons having equal content have also equal measures of area. The converse of this is also true. In order to prove the converse, let us consider two triangles, ABC and AB'C', having a common right angle at A. The measures of area of these two triangles are expressed by the formulae f of ABC equals 1/2 AB times AC. F of AB'C' equals 1/2 AB' times AC'. We now assume that these measures of area are equal to each other, and consequently we have AB times AC equals AB prime times AC prime, or AB is to AB prime as AC prime is to AC. From this proposition, it follows, according to Theorem 23, that the two straight lines BC prime and B prime C are parallel, and hence by Theorem 27, the two triangles BC prime B prime and BC prime C are of equal content. By the addition of the triangle ABC prime, it follows that the two triangles ABC and AB prime C prime are of equal content. We have then shown that two right triangles having the same measure of area are always of equal content. Take now any arbitrary triangle having the base G and the altitude h. Then, according to Theorem 27, it has equal content with a right triangle having the two sides G and H. Since the original triangle had evidently the same measure of area as the right triangle, it follows that, in the above consideration, the restriction to right triangles was not necessary. Hence, two arbitrary triangles with equal measures of area are also of equal content. Moreover, let us suppose P to be any polygon having the measure of area G, and let P be decomposed into n triangles having respectively the measures of area G1, G2, G3, Gn. Then we have G equal to G1 plus G2 plus G3 plus plus Gn. Construct now a triangle ABC having the base AB equal G and the altitude h equal 1. Take upon the base of this triangle the points A1, A2, A, n minus 1, so that G1 is equal to AA1, G2 equals A1, A2, G n minus 1 equal A n minus 2, A n minus 1, Gn equals A n minus 1 B. Since the triangles composing the polygon P have, respectively, the same measures of area as the triangles A1C, A1, A2C, A n minus 2, A n minus 1 C, A n minus 1 BC, it follows from what has already been demonstrated that they have also the same content as these triangles. Consequently, the polygon P and a triangle having the base G and the altitude h equal 1 are of equal content. From this it follows, by the application of Theorem 24, that two polygons having equal measures of area are always of equal content. We can now combine the proposition of this section with that demonstrated in the last, and thus obtain the following theorem. Theorem 30. Two polygons of equal content have always equal measures of area. Conversely, two polygons having equal measures of area are always of equal content. In particular, if two rectangles are of equal content and have one side in common, then their remaining sides are respectively congruent. Hence, we have the following proposition. Theorem 31. If we decompose a rectangle into several triangles by means of straight lines, and then omit one of these triangles, we can no longer make up completely the rectangle from the triangles which remain. This theorem has been demonstrated by F. Schur and by W. Killing, but by making use of the axiom of Archimedes. By O. Stolz, it has been regarded as an axiom. In the foregoing discussion, it has been shown that it is completely independent of the axiom of Archimedes. However, when we disregard the axiom of Archimedes, this theorem, 31, is not sufficient of itself to enable us to demonstrate Euclid's theorem concerning the equality of altitudes of triangles having equal content and equal basis, theorem 28. In the demonstration of theorems 28, 29, and 30, we have employed essentially the algebra of segments introduced in section 15, page 29. And as this depends substantially upon Pascal's theorem, theorem 21, we see that this theorem is really the cornerstone in the theory of areas. We may, by the aid of theorems 27 and 28, easily establish the converse of Pascal's theorem. Of two polygons, P and Q, we call P the smaller or larger in content, according as the measure of area f of P is less or greater than the measure of area f of Q. From what has already been said, it is clear that the notions equal content, smaller content, larger content are mutually exclusive. Moreover, we easily see that a polygon, which lies wholly within another polygon, must always be of smaller content than the exterior one. With this, we have established the important theorems in the theory of areas. End of section 21. Chapter 5, Section 22 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 22, Desargues' Theorem and its demonstration for plane geometry by aid of the axioms of congruence. Of the axioms given in sections 1 through 8, pages 1 through 14, those of groups 2 through 5 are in part linear and in part plane axioms. Axioms 3 through 7 of group 1 are the only space axioms. In order to show clearly the significance of these axioms of space, let us assume a plane geometry and investigate in general the conditions for which this plane geometry may be regarded as a part of a geometry of space, in which at least the axioms of groups 1 through 3 are all fulfilled. Upon the basis of the axioms of groups 1 through 3, it is well known that the so-called theorem of Desargues may be easily demonstrated. This theorem relates to points of intersection in a plane. Let us assume, in particular, that the straight line upon which are situated the points of intersection of the homologous sides of the two triangles is the straight line which we call the straight line at infinity. We will designate the theorem which arises in this case, together with its converse, as the theorem of Desargues. This theorem is as follows. Theorem 32, Desargues' theorem. When two triangles are so situated in a plane that their homologous sides are respectively parallel, then the lines joining the homologous vertices pass through one and the same point, or are parallel to one another. Conversely, if two triangles are so situated in a plane that the straight lines joining the homologous vertices intersect in a common point, or are parallel to one another, and furthermore, if two pairs of homologous sides are parallel to each other, then the third sides of the two triangles are also parallel to each other. As we have already mentioned, Theorem 32 is a consequence of the axioms 1 through 3. Because of this fact, the validity of Desargues' theorem in the plane is, in any case, a necessary condition that the geometry of this plane may be regarded as a part of a geometry of space in which the axioms of groups 1 through 3 are all fulfilled. Let us assume, as in sections 13 through 21, pages 23 through 45, that we have a plane geometry in which the axioms 1, 1 through 2, and 2 through 4 all hold, and also that we have introduced in this geometry an algebra of segments conforming to section 15. Now, as has already been established in section 17, there may be made to correspond to each point in the plane a pair of segments xy, and to each straight line a ratio of 3 segments u, v, w, so that the linear equation ux plus vy plus w equals 0 expresses the condition that the point is situated upon the straight line. The system composed of all the segments in our geometry forms, according to section 17, a domain of numbers for which the properties 1 through 16 enumerated in section 13 are valid. We can, therefore, by means of this domain of numbers, construct a geometry of space in a manner similar to that already employed in sections 9 or in section 12, where we made use of the systems of numbers omega and omega of t, respectively. For this purpose, we assume that a system of 3 segments, x, y, z, shall represent a point, and that the ratio of 4 segments u, v, w, r shall represent a plane, while a straight line is defined as the intersection of 2 planes. Hence, the linear equation ux plus vy plus wz plus r equals 0 expresses the fact that the point x, y, z lies in the plane u, v, w, r. Finally, we determine the arrangement of the points upon a straight line, or the points of a plane with respect to a straight line situated in this plane, or the arrangement of the points in space with respect to a plane by means of inequalities in a manner similar to the method employed for the plane in section 9. Since we obtain again the original plane geometry by putting z equals 0, we know that our plane geometry can be regarded as a part of geometry of space. Now, the validity of Desargues' theorem is, according to the above considerations, a necessary condition for this result. Hence, in the assumed plane geometry, it follows that Desargues' theorem must also hold. It will be seen that the result just stated may also be deduced without difficulty from Theorem 23 in the theory of proportion. End of section 22. Chapter 5, Section 23, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 23. The impossibility of demonstrating Desargues' theorem for the plane without the help of the axioms of congruence. We shall now investigate the question whether or no, in plane geometry, Desargues' theorem may be deduced without the assistance of the axioms of congruence. This leads us to the following result. Theorem 33. A plane geometry exists in which the axioms 1, 1 through 2, 2, 3, 4, 1 through 5, 5, that is to say, all linear and all plane axioms with the exception of axiom 4, 6 of congruence are fulfilled, but in which the theorem of Desargues, Theorem 32, is not valid. Desargues' theorem is not, therefore, a consequence solely of the axioms mentioned, for its demonstration necessitates either the space axioms or all of the axioms of congruence. Proof. Select in the ordinary plane geometry, the possibility of which has already been demonstrated in section 9, pages 15 through 17, any two straight lines perpendicular to each other as the axes of x and y. Construct about the origin O of this system of coordinates an ellipse having the major and minor axes equal to 1 and 1/2 respectively. Finally, let F denote the point situated upon the positive x-axis at the distance 3/2 from O. Consider all of the circles which cut the ellipse in 4 real points. These points may be either distinct or in any way coincident. Of all the points situated upon these circles, we shall attempt to determine the one which lies upon the x-axis farthest from the origin. For this purpose, let us begin with an arbitrary circle cutting the ellipse in 4 distinct points and intersecting the positive x-axis in the point C. Suppose this circle then turned about the point C in such a manner that 2 or more of the 4 points of intersection with the ellipse finally coincide in a single point A, while the rest of them remain real. Increase now the resulting tangent circle in such a way that A always remains a point of tangency with the ellipse. In this way, we obtain a circle which is either tangent to the ellipse in also a second point B, or which has, with the ellipse, a 4-point contact in A. Moreover, this circle cuts the positive x-axis in a point more remote than C. The desired farthest point will accordingly be found among those points of intersection of the positive x-axis by circles lying exterior to the ellipse and being doubly tangent to it. All such circles must lie, as we can easily see, symmetrically with respect to the y-axis. Let A, B be the coordinates of any point on the ellipse. Then, an easy calculation shows that the circle, which is symmetrical with respect to y-axis and tangent to the ellipse at this point, cuts off from the positive x-axis the segment x equal the absolute value of the square root of the quantity 1 plus 3b squared. The greatest possible value of this expression occurs for b equal 1/2. And hence is equal to 1/2 the absolute value of the square root of 7. Since the point on the x-axis which we have denoted by F has for its abscissa the value 3/2 greater than 1/2 the absolute value of the square root of 7, it follows that, among the circles cutting the ellipse 4 times, there is certainly none which passes through the point F. We will now construct a new plane geometry in the following manner. As points in this new geometry, let us take the points of the xy plane. We will define a straight line of our new geometry in the following manner. Every straight line of the xy plane, which is either tangent to the fixed ellipse or does not cut it at all, is taken unchanged as a straight line of the new geometry. However, when any straight line G of the xy plane cuts the ellipse, say in the points P and Q, we will then define the corresponding straight line of the new geometry as follows. Construct a circle passing through the points P and Q and the fixed point F. From what has just been said, this circle will have no other point in common with the ellipse. We will now take the broken line consisting of the arc PQ just mentioned and the 2 parts of the straight line G extending outward indefinitely from the points P and Q as the required straight line in our new geometry. Let us suppose all of the broken lines constructed which correspond to straight lines of the xy plane. We have then a system of broken lines which, considered as straight lines of our new geometry, evidently satisfy the axioms 1 through 2, and 3. By a convention as to the actual arrangement of the points and the straight lines in our new geometry, we have also the axioms 2 fulfilled. Moreover, we will call two segments AB and A'B' congruent in this new geometry if the broken line extending between A and B has equal length, in the ordinary sense of the word, with the broken line extending from A' to B'. Finally, we need a convention concerning the congruence of angles. So long as neither of the vertices of the angles to be compared lies upon the ellipse, we call the two angles congruent to each other if they are equal in the ordinary sense. In all other cases, we make the following convention. Let A, B, C be points which follow one another in this order upon a straight line of our new geometry. And let A', B', C' be also points which lie in this order upon another straight line of our new geometry. Let D be a point lying outside of the straight line A, B, C, and D' be a point outside of the straight line A', B', C'. We will now say that, in our new geometry, the angles between these straight lines fulfill the congruences, the angle ABD congruent to the angle A', B', D', and the angle CBD congruent to the angle C', B', D', whenever the natural angles between the corresponding broken lines of the ordinary geometry fulfill the proportion, the angle ABD is to the angle CBD as the angle A', B', D' is to the angle C', B', D'. These conventions render the axioms 4, 1 through 5, and 5 valid. In order to see that Desargues' theorem does not hold for our new geometry, let us consider the following three ordinary straight lines of the xy plane, namely the axis of x, the axis of y, and the straight line joining the 2 points of the ellipse, 3/5, 2/5, and -3/5, -2/5. Since these three ordinary straight lines pass through the origin, we can easily construct two triangles so that their vertices shall lie respectively upon these three straight lines, and their homologous sides shall be parallel, and all three sides shall lie exterior to the ellipse. As we may see from Figure 40, or show by an easy calculation, the broken lines arising from the three straight lines in question do not intersect in a common point. Hence it follows that Desargues' theorem certainly does not hold for this particular plane geometry, in which we have constructed the two triangles just considered. This new geometry serves at the same time as an example of a plane geometry in which axioms 1, 1 through 2, 2, 3, 4, 1 through 5, 5 all hold, but which cannot be considered as a part of a geometry of space. End of section 23. Chapter 5, Section 24 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 24, Introduction of an algebra of segments based upon Desargues' theorem and independent of the axioms of congruence. In order to see fully the significance of Desargues' theorem, Theorem 32, let us take as the basis of our consideration a plane geometry where all of the axioms 1, 1 through 2, 2, 3 are valid. That is to say, where all of the plane axioms of the first three groups hold, and then introduce into this geometry, in the following manner, a new algebra of segments independent of the axioms of congruence. Taken the plane, two fixed straight lines intersecting in O, and consider only such segments as have O for their origin and their other extremity in one of the fixed lines. We will regard the point O itself as a segment and call it the segment O. We will indicate this fact by writing OO equals 0 or 0 equals OO. Let E and E prime be two definite points situated respectively upon the two fixed straight lines through O. Then define the two segments OE and OE prime as the segment 1 and write accordingly OE equals OE prime equals 1 or 1 equals OE equals OE prime equation 1. We will call the straight line EE prime for brevity the unit line. If, furthermore, A and A prime are points upon the straight lines OE and OE prime respectively, and if the straight line AA prime joining them is parallel to EE prime, then we will say that the segments OA and OA prime are equal to one another and write OA equals OA prime or OA prime equals OA. In order now to define the sum of the segments A equals OA and B equal OB, we construct AA prime parallel to the unit line EE prime and draw through A prime a parallel to OE and through B a parallel to OE prime. Let these two parallels intersect in A double prime. Finally, draw through A double prime a straight line parallel to the unit line EE prime. Let this parallel cut the two fixed lines OE and OE prime in C and C prime respectively. Then C equal OC equal OC prime is called the sum of the segments A equal OA and B equal OB. We indicate this by writing C equals A plus B, or A plus B equals C. In order to define the product of a segment A equal OA by a segment B equal OB, we make use of exactly the same construction as employed in section 15, except that in the place of the sides of a right angle, we make use here of the straight lines OE and OE prime. The construction is consequently as follows. Determine upon OE prime a point A prime, so that AA prime is parallel to the unit line EE prime, and join E with A prime. Then draw through B a straight line parallel to EA prime. This parallel will intersect the fixed straight line OE prime in the point C prime, and we call C equal OC prime the product of the segment A equal OA by the segment B equal OB. We indicate this relation by writing C equal AB or AB equal C. End of section 24. Chapter 5. Section 25 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5. Desargues' Theorem. Section 25. The commutative and the associative law of addition for our new algebra of segments. In this section, we shall investigate the laws of operation as enumerated in section 13, in order to see which of these hold for our new algebra of segments, when we base our considerations upon a plane geometry in which axioms 1 through 2, 2 through 3 are all fulfilled, and, moreover, in which Desargues' theorem also holds. First of all, we shall show that, for the addition of segments as defined in section 24, the commutative law A plus B equals B plus A holds, Let A equal OA equal OA prime, B equal OB equal OB prime. Hence, AA prime and BB prime are, according to our convention, parallel to the unit line. Construct the points A double prime and B double prime by drawing A prime A double prime and B prime B double prime parallel to OA, and also AB double prime and BA prime parallel to OA prime. We see at once that the line A double prime B double prime is parallel to AA prime, as the commutative law requires. We shall show the validity of this statement by the aid of Desargues' theorem in the following manner. Denote the point of intersection of A B double prime and A prime A double prime by F, and that of B A double prime and B prime B double prime by D. Then in the triangles A prime F and B prime D, the homologous sides are parallel to each other. By Desargues' theorem, it follows that the 3 points O, F, D lie in a straight line. In consequence of this condition, the 2 triangles OA prime and DB double prime A double prime lie in such a way that the lines joining the corresponding vertices pass through the same point F. And since the homologous sides OA and DB double prime, as also OA prime and DA double prime, are parallel to each other, then, according to the second part of Desargues' theorem, Theorem 32, the third sides, AA prime and B double prime A double prime, are parallel to each other. To prove the associative law of addition, A plus the quantity B plus C equal the quantity A plus B plus C, we shall make use of figure 44. In consequence of the commutative law of addition just demonstrated, the above formula states that the straight line A double prime B double prime must be parallel to the unit line. The validity of this statement is evident since the shaded part of figure 44 corresponds exactly with figure 43. End of section 25. Chapter 5, Section 26 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 26, the associative law of multiplication and the 2 distributive laws for the new algebra of segments. The associative law of multiplication, A times the quantity BC equals the quantity AB times C, has also a place in our new algebra of segments. Let there be given upon the first of 2 fixed straight lines through O, the segments 1 equal OA, B equal OC, C equal OA prime. And upon the second of these straight lines, the segments A equal OG, B equal OB. In order to construct the segments BC equal OB prime and BC equal OC prime, AB equal OD, the quantity AB times C equal OD prime, in accordance with section 24, draw A prime B prime parallel to AB, B prime C prime parallel to BC, CD parallel to AG, and A prime D prime parallel to AD. We see at once that the given law amounts to the same as saying that CD must also be parallel to C prime D prime. Denote the point of intersection of the straight lines A prime D prime and B prime C prime by F prime, and that of the straight lines AD and BC by F. Then the triangles ABF and A'B'F' have their homologous sides parallel to each other, and according to Desargues' theorem, the 3 points O, F, F' must lie in a straight line. Because of these conditions, we can apply the second part of Desargues' theorem to the two triangles CDF and C'D'F', and hence show that, in fact, CD is parallel to C'D'. Finally, upon the basis of Desargues' theorem, we shall show that the two distributive laws, A times the quantity B plus C equals AB plus AC, and the quantity A plus B times C equals AC plus BC, hold for our algebra of segments. In the proof of the first one of these laws, we shall make use of figure 46. In this figure, we have B equal OA prime, C equal OC prime, AB equal OB prime, AB equal OA double prime, AC equal OC double prime, etc. In the same figure, B double prime D sub 2 is parallel to C double prime D sub 1, which is parallel to the fixed straight line OA prime. And B prime D sub 1 is parallel to C prime D sub 2, which is parallel to the fixed straight line OA double prime. Moreover, we have A prime A double prime parallel to C prime C double prime, and A prime B double prime parallel to B prime A double prime, parallel to F prime D sub 2, parallel to F double prime D sub 1. Our proposition amounts to asserting that we must necessarily have also F prime F double prime parallel to A prime A double prime and to C prime C double prime. We construct the following auxiliary lines: F double prime J parallel to the fixed straight line OA prime, F prime J parallel to the fixed straight line OA double prime. Let us denote the points of intersection of the straight lines C double prime D sub 1 and C prime D sub 2, C double prime D sub 1 and F prime J, C prime D sub 2 and F double prime J by G, H sub 1, H sub 2, respectively. Finally, we obtain the other auxiliary lines indicated in the figure by joining the points already constructed. In the two triangles A prime B double prime C double prime and F prime D sub 2 G, the straight lines joining homologous vertices are parallel to each other. According to the second part of Desargues' theorem, it follows, therefore, that A prime C double prime is parallel to F prime G. In the two triangles A prime C double prime F double prime and F prime G H sub 2, the straight lines joining the homologous vertices are also parallel to each other. From the properties already demonstrated, it follows by virtue of the second part of Desargues' theorem that we must have A prime F double prime parallel to F prime H sub 2. Since in the two horizontally shaded triangles OA prime F prime and J H sub 2 F prime, the homologous sides are parallel, Desargues' theorem shows that the three straight lines joining the homologous vertices, namely OJ, A prime H sub 2, F double prime F prime, equation 2, all intersect in one and the same point, say in P. In the same way, we have necessarily A double prime F prime parallel to F double prime H sub 1, and since in the two obliquely shaded triangles OA double prime F prime and J H sub 1 F double prime, the homologous sides are parallel, then in consequence of Desargues' theorem, the three straight lines joining the homologous vertices, namely OJ, A double prime H sub 1, F prime F double prime, all intersect likewise in the same point, namely in point P. Moreover, in the triangles OA prime A double prime and J H sub 2 H sub 1, the straight lines joining the homologous vertices all pass through this same point P, and consequently it follows that we have H sub 1 H sub 2 parallel to A prime A double prime, and therefore H sub 1 H sub 2 parallel to C prime C double prime. Finally, let us consider the figure F double prime H sub 2 C prime C double prime H sub 1 F prime F double prime. Since in this figure we have F double prime H sub 2 parallel to C prime F prime parallel to C double prime H sub 1, G H sub 2 C prime parallel to F double prime C double prime parallel to H sub 1 F prime, C prime C double prime parallel to H sub 1 H sub 2, we recognize here again figure 43, which we have already made use of in section 25 to prove the commutative law of addition. The conclusions, analogous to those which we reached there, show that we must have F prime F double prime parallel to H sub 1 H sub 2, and consequently we must have also F prime F double prime parallel to A prime A double prime, which result concludes our demonstration. To prove the second formula of the distributive law, we make use of an entirely different figure, figure 47. In this figure we have 1 equal OD, A equal OA, A equal OB, B equal OG, C equal OD prime, AC equal OA prime, AC equal OB prime, BC equal OG prime, etc. And furthermore, we have GH parallel to G prime H prime, parallel to the fixed line OA, GH parallel to A prime H prime, parallel to the fixed line OB. We have also AB parallel to A prime B prime, BD parallel to B prime D prime, DG parallel to D prime G prime, HJ parallel to H prime J prime. That which we are to prove amounts then to demonstrating that dj must be parallel to d prime j prime. Denote the points in which BD and GD intersect the straight line AH by C and F, respectively, and the points in which B prime D prime and G prime D prime intersect the straight line A prime H prime by C prime and F prime, respectively. Finally, draw the auxiliary lines Fj and F prime J prime, indicated in the figure by dotted lines. In the triangles ABC and A prime B prime C prime, the homologous sides are parallel, and consequently, by Desargues' theorem, the 3 points OC, C prime lie on a straight line. Then, by considering in the same way the triangles CDF and CD prime F prime, it follows that the points OF, F prime lie upon the same straight line, and likewise, from a consideration of the triangles FGH and F prime G prime H prime, we find the points OH, H prime to be situated on a straight line. Now, in the triangles FHJ and F prime H prime J prime, the straight lines joining the homologous vertices all pass through the same point O, and hence, as a consequence of the second part of Desargues' theorem, the straight lines Fj and F prime J prime must also be parallel to each other. Finally, a consideration of the triangles DFJ and D prime F prime J prime shows that the straight lines dj and d'j' are parallel to each other, and with this our proof is completed. End of section 26. Chapter 5, Section 27 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 27, Equation of the straight line based upon the new algebra of segments. In sections 24 through 26, we have introduced into the plane geometry an algebra of segments, in which the commutative law of addition and that of multiplication, as well as the two distributive laws, hold. This was done upon the assumption that the axioms cited in section 24, as well as the theorem of Desargues, were valid. In this section, we shall show how an analytical representation of the point and the straight line in the plane is possible upon the basis of this algebra of segments. Definition: take the two given fixed straight lines lying in the plane and intersecting in O as the axis of x and y, respectively. Let us suppose any point P of the plane determined by the two segments xy, which we obtain upon the x and y axis, respectively, by drawing through P parallels to these axes. These segments are called the coordinates of the point P. Upon the basis of this new algebra of segments, and by aid of Desargues' theorem, we shall deduce the following proposition. Theorem 34. The coordinates xy of a point on an arbitrary straight line always satisfy an equation in these segments of the form ax plus by plus c equals 0. In this equation, the segments a and b stand necessarily to the left of the coordinates x and y. The segments a and b are never both 0, and c is an arbitrary segment. Conversely, every equation in these segments and of this form represents always a straight line in the plane geometry under consideration. Proof: suppose that the straight line L passes through the origin O. Furthermore, let C be a definite point upon L, different from O, and P any arbitrary point of L. Let OA and OB be the coordinates of C, and XY be the coordinates of P. We will denote the straight line joining the extremities of the segments XY by G. Finally, through the extremity of the segment 1, laid off on the x-axis, draw a straight line H parallel to AB. This parallel cuts off upon the y-axis the segment E. From the second part of Desargues' theorem, it follows that the straight line G is also always parallel to AB. Since G is always parallel to H, it follows that the coordinates xy of the point P must satisfy the equation Ex equals G. Moreover, in figure 49, let L' be any arbitrary straight line in our plane. This straight line will cut off on the x-axis the segment C equal O'. Now, in the same figure, draw through O the straight line L parallel to L'. Let P' be an arbitrary point on the line L'. The straight line through P', parallel to the x-axis, intersects the straight line L in P and cuts off upon the y-axis the segment y equal OB. Finally, through P and P', let parallels to the y-axis cut off on the x-axis the segments x equal OA and x' equal OA'. We shall now undertake to show that the equation x prime equal x plus c is fulfilled by the segments in question. For this purpose, draw O prime c parallel to the unit line, and likewise CD parallel to the x-axis and AD parallel to the y-axis. Then, to prove our proposition amounts to showing that we must have necessarily A prime D parallel to O prime C. Let D prime be the point of intersection of the straight lines CD and A prime P prime, and draw O prime C prime parallel to the y-axis. Since in the triangles OCP and O prime C prime P prime, the straight lines joining the homologous vertices are parallel, it follows, by virtue of the second part of Desargues' theorem, that we must have CP parallel to C prime P prime. In a similar way, a consideration of the triangles ACP and A prime C prime P prime shows that we must have AC parallel to A prime C prime. Since in the triangles ACD and C prime A prime O prime, the homologous sides are parallel to each other, it follows that the straight lines AC prime, CA prime, and DO prime intersect in a common point. A consideration of the triangles C prime A prime D and ACO prime then shows that A prime D and CO prime are parallel to each other. From the two equations already obtained, namely EX equal Y and X prime equal X plus C, equation 3, follows at once the equation EX prime equal Y plus EC, equation 4. If we denote, finally, by n, the segment which added to the segment 1 gives the segment 0, then, from this last equation, we may easily deduce the following: EX prime plus NY plus NEC equals 0, equation 5, and this equation is of the form required by Theorem 34. We can now show that the second part of the theorem is equally true for every linear equation AX plus BY plus C equals 0, equation 6, may evidently be brought into the required form EX plus NY plus NEC equals 0, equation 7, by a left-sided multiplication by a properly chosen segment. It must be expressly stated, however, that by our hypothesis, an equation of segments of the form XA plus YB plus C equals 0, equation 8, where the segments A, B stand to the right of the coordinates x, y, does not in general represent a straight line. In section 30, we shall make an important application of Theorem 34. End of section 27. Chapter 5, Section 28 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 28, the totality of segments regarded as a complex number system. We see immediately that, for the new algebra of segments established in Section 24, Theorems 1 through 6 of Section 13 are fulfilled. Moreover, by aid of Desargues' theorem, we have already shown in Sections 25 and 26 that the laws 7 through 11 of operation, as given in Section 13, are all valid in this algebra of segments. With the single exception of the commutative law of multiplication, therefore, all of the theorems of connection hold. Finally, in order to make possible an order of magnitude of these segments, we make the following convention. Let A and B be any two distinct points of the straight line OE. Suppose then that the 4 points OEAB stand in conformity with axiom 2, 4 in a certain sequence. If this sequence is one of the following 6 possible ones, namely ABOE, AOBE, AOEB, OABE, OAEB, OEAB, then we will call the segment A equal OA smaller than the segment B equal OB and indicate the same by writing A less than B. On the other hand, if the sequence is one of the 6 following ones, namely BAOE, BOAE, BOEA, OBAE, OBEA, OEBA, then we will call the segment A equal OA greater than the segment B equal OB, and we write accordingly A greater than B. This convention remains in force whenever A or B coincides with O or E. Only then the coinciding points are to be regarded as a single point, and consequently we have only to consider the order of 3 points. Upon the basis of the axioms of Group 2, we can easily show also that, in our algebra of segments, the laws 13 through 16 of operation given in section 13 are fulfilled. Consequently, the totality of all the different segments forms a complex number system for which the laws 1 through 11, 13 through 16 of section 13 hold. That is to say, all of the usual laws of operation except the commutative law of multiplication and the theorem of Archimedes. We will call such a system, briefly, a Desarguesian number system. End of section 28. Chapter 5, Section 29. Of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5. Desargues' theorem. Section 29. Construction of a geometry of space by aid of a Desarguesian number system. Suppose we have given a Desarguesian number system D. Such a system makes possible the construction of a geometry of space in which axioms 1, 2, 3 are all fulfilled. In order to show this, let us consider any system of 3 numbers, x, y, z, of the Desarguesian number system D as a point, and the ratio of 4 such numbers, u, v, w, r, of which the first 3 are not 0, as a plane. However, the systems u, v, w, r, and au, av, aw, ar, where a is any number of D different from 0, represent the same plane. The existence of the equation ux plus vy plus wz plus r equals 0 expresses the condition that the point xyz shall lie in the plane u, v, w, r. Finally, we define a straight line by the aid of a system of 2 planes u prime v prime w prime r prime and u double prime v double prime w double prime r double prime, where we impose the condition that it is impossible to find in D 2 numbers a prime a double prime different from 0, such that we have simultaneously the relations a prime u prime equal a double prime u double prime, a prime v prime equal a double prime v double prime, a prime w prime equal a double prime w double prime. A point xyz is said to be situated upon this straight line u prime v prime w prime r prime, u double prime v double prime w double prime r double prime, if it is common to the two planes u prime v prime w prime r prime and u double prime v double prime w double prime r double prime. Two straight lines which contain the same points are not regarded as being distinct. By application of the laws 1 through 11 of section 13, which by hypothesis hold for the numbers of D, we obtain without difficulty the result that the geometry of space, which we have just constructed, satisfies all of the axioms of groups 1 and 3. In order that the axioms 2 of order may also be valid, we adopt the following conventions. Let x1, y1, z1, x2, y2, z2, x3, y3, z3 be any 3 points of a straight line, u prime, v prime, w prime, r prime, u double prime, v double prime, w double prime, r double prime. Then the point x2, y2, z2 is said to lie between the other two if we have fulfilled at least one of the 6 following double inequalities. x1 less than x2 less than x3, x1 greater than x2 greater than x3, equation 9, y1 less than y2 less than y3, y1 greater than y2 greater than y3, equation 10, z1 less than z2 less than z3, z1 greater than z2 greater than z3, equation 11. If one of the two double inequalities, law 1, exist, then we can easily conclude that either y1 equal y2 equal y3, or one of the two double inequalities, law 2, exist, and consequently either z1 equals z2 equals z3, or one of the double inequalities, law 3, must exist. In fact, from the equations u prime x sub I plus v prime y sub I plus w prime z sub I plus r prime equals 0, u double prime x sub I plus v double prime y sub I plus w double prime z sub I plus r double prime equals 0, I equal 1, 2, 3, we may obtain by a left-sided multiplication of these equations by numbers suitably chosen from D, and then adding the resulting equations, a system of equations of the form u triple prime x sub I plus v triple prime y sub I plus r triple prime equals 0, I equal 1, 2, 3. Equation 12. In this system, the coefficient v triple prime is certainly different from 0, since otherwise the three numbers x sub 1, x sub 2, x sub 3 would be mutually equal. From x sub 1 less than greater than x sub 2 less than greater than x sub 3, it follows that u triple prime x sub 1 less than equal greater than x triple prime u sub 2 less than equal greater than x triple prime u sub 3, and hence, as a consequence of equation 4, we have v triple prime y sub 1 plus r triple prime less than equal greater than v triple prime y sub 2 plus r triple prime less than equal greater than v triple prime y sub 3 plus r triple prime, and therefore v triple prime y sub 1 less than equal greater than v triple prime y sub 2 less than equal greater than v triple prime y sub 3. Since v triple prime is different from 0, we have y sub 1 less than equal greater than y sub 2 less than equal greater than y sub 3. In each of these double inequalities, we must take either the upper sign throughout, or the middle sign throughout, or the lower sign throughout. The preceding considerations show that in our geometry, the linear axioms 2, 1 through 4 of order are all valid. However, it remains yet to show that, In this geometry, the plane axiom 2, 5 is also valid. For this purpose, let a plane UVWR and a straight line UVWR U prime V prime W prime R prime in this plane be given. Let us assume that all of the points x, y, z of the plane UVWR, for which we have the expression u prime x plus v prime y plus w prime z plus r prime greater than or less than 0, lie respectively upon the one side or upon the other side of the given straight line. We have then only to show that this convention is in accordance with the preceding statements. This, however, is easily done. We have thus shown that all of the axioms groups 1, 2, 3 are fulfilled in the geometry of space, which we have obtained in the above indicated manner from the Desarguesian number system D. Remembering now that the theorem of Desargues is a consequence of the axioms 1, 2, 3, we see that the proposition just stated is exactly the converse of the result reached in section 28. End of section 29. Chapter 5, Section 30 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 5, Desargues' Theorem. Section 30, Significance of Desargues' Theorem. If, in a plane geometry, axioms 1, 1 through 2, 2, 3 are all fulfilled, and, moreover, if the theorem of Desargues holds, then, according to sections 24 through 28, it is always possible to introduce into this geometry an algebra of segments to which the laws 1 through 11, 13 through 16 of section 13 are applicable. We will now consider the totality of these segments as a complex number system and construct upon the basis of this system a geometry of space in accordance with section 29 in which all of the axioms 1, 2, 3 hold. In this geometry of space, we shall consider only the points x, y, 0 and those straight lines upon which only such points lie. We have then a plane geometry, which must, if we take into account the proposition established in section 27, coincide exactly with the plane geometry proposed at the beginning. Hence, we are led to the following proposition, which may be regarded as the objective point of the entire discussion of the present chapter. Theorem 35. If, in a plane geometry, axioms 1, 1 through 2, 2, 3 are all fulfilled, then the existence of Desargues' theorem is the necessary and sufficient condition that this plane geometry may be regarded as a part of a geometry of space in which all of the axioms 1, 2, 3 are fulfilled. The theorem of Desargues may be characterized for plane geometry as being, so to speak, the result of the elimination of the space axioms. The results obtained so far put us now in a position to show that every geometry of space in which axioms 1, 2, 3 are all fulfilled may be always regarded as a part of a geometry of any number of dimensions whatever. By a geometry of an arbitrary number of dimensions is to be understood the totality of all points, straight lines, planes, and other linear elements, for which the corresponding axioms of connection and of order, as well as the axiom of parallels, are all valid. End of section 30. Chapter 6, Section 31 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 6, Pascal's Theorem, Section 31. Two theorems concerning the possibility of proving Pascal's theorem. As is well known, Desargues' theorem, Theorem 32, may be demonstrated by the aid of Axioms 1, 2, 3, that is to say, by the use, essentially, of the axioms of space. In Section 23, we have shown that the demonstration of this theorem without the aid of the space axioms of Group 1 and without the axioms of congruence, Group 4, is impossible, even if we make use of the axiom of Archimedes. Upon the basis of the axioms 1, 1 through 2, 2, 3, 4, and hence by the exclusion of the axioms of space, but with the assistance, essentially, of the axioms of congruence, we have, in Section 14, deduced Pascal's theorem, and consequently, according to Section 22, also Desargues' theorem. The question arises as to whether Pascal's theorem can be demonstrated without the assistance of the axioms of congruence. Our investigation will show that in this respect Pascal's theorem is very different from Desargues' theorem, for in the demonstration of Pascal's theorem, the admission or exclusion of the axiom of Archimedes is of decided influence. We may combine the essential results of our investigation in the two following theorems. Theorem 36, Pascal's theorem, Theorem 21, may be demonstrated by means of the axioms 1, 2, 3, 5, that is to say, without the assistance of the axioms of congruence and with the aid of the axiom of Archimedes. Theorem 37, Pascal's theorem, Theorem 21, cannot be demonstrated by means of axioms 1, 2, 3 alone, that is to say, by exclusion of the axioms of congruence and also the axiom of Archimedes. In the statement of these two theorems, we may, by virtue of the general theorem 35, replace the space axioms 1, 3 through 7 by the plain condition that Desargues' theorem, Theorem 32, shall be valid. End of Section 31. Chapter 6, Section 32 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 6, Pascal's Theorem, Section 32, the commutative law of multiplication for an Archimedean number system. The demonstration of theorems 36 and 37 rest essentially upon certain mutual relations concerning the laws of operation and the fundamental propositions of arithmetic, a knowledge of which is of interest of itself. We will state the two following theorems. Theorem 38. For an Archimedean number system, the commutative law of multiplication is a necessary consequence of the remaining laws of operation. That is to say, if a number system possesses the properties 1 through 11, 13 through 17 given in Section 13, it follows necessarily that this system satisfies also Formula 12. Proof. Let us observe, first of all, that if A is an arbitrary number of the system, and if n equal 1 plus 1 plus ... plus 1 is a positive integral rational number, then for n and a the commutative law of multiplication always holds. In fact, we have an equal a times the quantity 1 plus 1 plus ... plus 1. equals a times 1 plus a times 1 plus dot 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 plus a times 1 equals a plus dot 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 plus a. And likewise, Na equals the quantity 1 plus dot 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 plus 1 times a equals 1 times a plus 1 times a plus dot 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 plus 1 times a equals a plus dot 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 plus a. Suppose now, in contradiction to our hypothesis, a, b to be numbers of this system for which the commutative law of multiplication does not hold. It is then at once evident that we may make the assumption that we have a greater than 0, b greater than 0, ab minus ba greater than 0. By virtue of condition 6 of section 13, there exists a number c greater than 0, such that the quantity a plus b plus 1 times c equals ab minus ba. Finally, if we select a number d, satisfying simultaneously the inequalities d greater than 0, d less than 1, d less than c, and denote by m and n two such integral rational numbers greater than equals 0 that we have respectively md less than a less than equal the quantity m plus 1 times d, and nd less than b less than equal the quantity n plus 1 times d. Then the existence of the numbers m and n is an immediate consequence of the theorem of Archimedes, Theorem 17, section 13. Recalling now the remark made at the beginning of this proof, we have by multiplication of the last inequalities ab less than equal mnd squared plus the quantity m plus n plus 1 times d squared, ba greater than mnd squared, and hence by subtraction ab minus ba less than equal the quantity m plus n plus 1 times d squared. We have, however, md less than a, nd less than b, d less than 1, and consequently the quantity m plus n plus 1 times d is less than a plus b plus 1, i.e., ab minus ba less than the quantity a plus b plus 1 times d, or since d is less than c, we have ab minus ba less than the quantity a plus b plus 1 times c. This inequality stands in contradiction to the definition of the number c, and hence the validity of the Theorem 38 follows. End of section 32. Chapter 6, Section 33 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 6, Pascal's Theorem. Section 33, the commutative law of multiplication for a non-Archimedean number system. Theorem 39. For a non-Archimedean number system, the commutative law of multiplication is not a necessary consequence of the remaining laws of operation. That is to say, there exists a system of numbers possessing the properties 1 through 11, 13 through 16, mentioned in section 13, but for which the commutative law 12 of multiplication is not valid. A desarguesian number system, in the sense of section 28, is such a system. Proof: let T be a parameter, and T any expression containing a finite or infinite number of terms, say of the form T equal R sub 0 T to the nth power plus r sub 1 t to the n plus 3 plus r sub 2 t to the n plus 2 plus r sub 3 t to the n plus 3 plus ... where r sub 0 not equal to 0, r sub 1, r sub 2, ... are arbitrary rational numbers, and n is an arbitrary integral rational number greater than, equal to, or less than 0. Moreover, let S be another parameter, and S any expression having a finite or infinite number of terms, say of the form S equal S to the mth power t sub 0 plus S to the m plus 1 t sub 1 plus S to the m plus 2 t sub 2 plus ... where t sub 0 not equal to 0, t sub 1, t sub 2, ... denote arbitrary expressions of the form t, and m is again an arbitrary integral rational number less than, equal, greater than 0. We will regard the totality of all the expressions of the form S as a complex number system, omega of S, t, for which we will assume the following laws of operation. Namely, we will operate with S and t according to the laws 7 through 11 of section 13, as with parameters, while in place of rule 12, we will apply the formula Ts equal to 2st, equation 13. If now S prime, S double prime are any two expressions of the form S, say S prime equal S to the m prime t sub 0 prime plus S to the m prime plus 1 t sub 1 prime plus S to the m prime plus 2 t sub 2 prime plus ... S double prime equal S to the m double prime power times t sub 0 double prime plus S to the m double prime plus 1 t sub 1 double prime plus S to the m double prime plus 2 t sub 2 double prime plus ... Then, by combination, we can evidently form a new expression, S prime plus S double prime, which is of the form S, and is, moreover, uniquely determined. This expression, S prime plus S double prime, is called the sum of the numbers represented by S prime and S double prime. By the multiplication of the two expressions S prime and S double prime, term by term, we obtain another expression of the form S prime S double prime equal S to the m prime t sub 0 prime S to the m double prime t sub 0 double prime plus the quantity S to the m prime t sub 0 prime S to the m double prime plus 1 t sub 1 double prime minus S to m prime plus 1 t sub 1 prime S to the m double prime t sub 0 double prime close paren plus the quantity S to the m prime t sub 0 prime S to the m double prime plus 2 t sub 2 double prime plus S to the m prime plus 1 t sub 1 prime S to the m double prime plus 1 t sub 1 double prime plus S to the m prime plus 2 t sub 2 prime S to the m double prime t sub 0 double prime close paren plus ... This expression, by the aid of Formula 1, is evidently a definite single-valued expression of the form S, and we will call it the product of the numbers represented by S prime and S double prime. This method of calculation shows at once the validity of the laws 1 through 5 given in section 13 for calculating with numbers. The validity of law 6 in that section is also not difficult to establish. To this end, let us assume that S prime equal S to the m prime power times t sub 0 prime plus S to the m prime plus 1 t sub 1 prime plus S to the m prime plus 2 t sub 2 prime plus ... and S triple prime equal S to the m triple prime power t sub 0 triple prime plus S to the m triple prime plus 1 t sub 1 triple prime plus s to the m triple prime plus 2 t sub 2 triple prime are two expressions of the form s, and let us suppose further that the coefficients r sub 0 prime of t sub 0 prime is different from 0. By equating the like powers of s in the two members of the equation s prime s double prime equal s triple prime, we find, first of all, in a definite manner an integral number m double prime s exponent, and then such a succession of expressions t sub 0 double prime, comma t sub 1 double prime, comma t sub 2 double prime, that by aid of Formula 1, the expression s double prime equal s to the m double prime t sub 0 double prime plus s to the m double prime plus 1 t sub 1 double prime plus s to the m double prime plus 2 t sub 2 double prime satisfies equation 2. With this, our theorem is established. In order, finally, to render possible an order of sequence of the numbers of our system, omega of s comma t, we make the following conventions. Let a number of this system be called greater or less than 0, according as in the expression s, which represents it, the first coefficient r sub 0 of t sub 0 is greater or less than 0. Given any two numbers, a, b, of the complex number system under consideration, we say that a less than b or a greater than b, according as we have a minus b less than 0 or greater than 0. It is seen immediately that with these conventions, the laws 13 through 16 of section 13 are valid. That is to say, omega of s comma t is a desarguesian number system. See section 28. As equation 1 shows, law 12 of section 13 is not fulfilled by our complex number system, and consequently, the validity of theorem 39 is fully established. In conformity with theorem 38, Archimedes' theorem, theorem 17, section 13, does not hold for the number system omega of s comma t, which we have just constructed. We wish also to call attention to the fact that the number system omega of s comma t, as well as the systems omega and omega of t made use of in section 9 and section 12 respectively, contains only an enumerable set of numbers. End of section 33. Chapter 6, Section 34 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 6, Pascal's Theorem. Section 34, Proof of the two propositions concerning Pascal's theorem. Non-pascalian geometry. If, in a geometry of space, all of the axioms 1, 2, 3 are fulfilled, then Desargues' theorem, theorem 32, is also valid, and consequently, according to sections 24 through 26, pages 50 through 58, it is possible to introduce into this geometry an algebra of segments for which the rules 1 through 11, 13 through 16 of section 13 are all valid. If we assume now that the axiom 5 of Archimedes is valid for our geometry, then evidently Archimedes' theorem, theorem 17 of section 13, also holds for our algebra of segments, and consequently, by virtue of theorem 38, the commutative law of multiplication is valid. Since, however, the definition of the product of two segments as introduced in section 24, figure 42, and which is the definition here also under discussion, agrees with the definition in section 15, figure 22, it follows from the construction made in section 15 that the commutative law of multiplication is here nothing else than Pascal's theorem. Consequently, the validity of theorem 36 is established. In order to demonstrate theorem 37, let us consider again the Desarguesian number system omega of s, t, introduced in section 33, and construct, in the manner described in section 29, a geometry of space for which all of the axioms 1, 2, 3 are fulfilled. However, Pascal's theorem will not hold for this geometry, for the commutative law of multiplication is not valid in the Desarguesian number system omega of st. According to theorem 36, the non-pascalian geometry is then necessarily also a non-archimedean geometry. By adopting the hypothesis we have, it is evident that we cannot demonstrate Pascal's theorem, providing we regard our geometry of space as part of a geometry of an arbitrary number of dimensions in which, besides the points, straight lines, and planes, still other linear elements are present, and providing there exists for these elements a corresponding system of axioms of connection and of order, as well as the axiom of parallels. End of section 34. Chapter 6, Section 35, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 6, Pascal's Theorem. Section 35. The demonstration by means of the theorems of Pascal and Desargues of any theorem relating to points of intersection. Every proposition relating to points of intersection in a plane has necessarily the form: select, first of all, an arbitrary system of points and straight lines satisfying respectively the condition that certain ones of these points are situated on certain ones of the straight lines. If, in some known manner, we construct the straight lines joining the given points and determine the points of intersection of the given lines, we shall obtain finally a definite system of three straight lines, of which our proposition asserts that they all pass through the same point. Suppose we now have a plane geometry in which all of the axioms 1 through 2, 5 are valid. According to section 17, pages 33 through 35, we may now find, by making use of a rectangular pair of axes, for each point a corresponding pair of numbers, x, y, and for each straight line a ratio of three definite numbers, u, v, w. Here the numbers x, y, u, v, w are all real numbers of which u and v cannot both be 0. The condition showing that the given point is situated upon the given straight line, namely ux plus vy plus w equals 0, equation 14, is an equation in the ordinary sense of the word. Conversely, in case x, y, u, v, w are numbers in the algebraic domain omega of section 9, and u, v are not both 0, we may certainly assume that each pair of numbers, x, y, gives a point, and that each ratio of three numbers, u, v, w, gives a straight line in the geometry in question. If, for all the points and straight lines which occur in connection with any theorem relating to intersections in a plane, we introduce the corresponding pairs and triples of numbers, then such a theorem asserts that a definite expression A of P1, P2, P sub r with real coefficients and depending rationally upon certain parameters P1, P2, P sub r always vanishes as soon as we put for each of these parameters a number of the main omega considered in section 9. We conclude from this that the expression A of P1, P2, P sub r must also vanish identically in accordance with the laws 7 through 12 of section 13. Since, according to section 32, Desargues' theorem holds for the geometry in question, it follows that we certainly can make use of the algebra of segments introduced in section 24, and because Pascal's theorem is equally valid in this case, the commutative law of multiplication is also. Hence, for this algebra of segments, all of the laws 7 through 12 of section 13 are valid. If we take as our axes in this new algebra of segments the coordinate axes already used and consider the unit points E, E' as suitably established, we see that the new algebra of segments is nothing else than the system of coordinates previously employed. In order to show that, for the new algebra of segments, the expression A of P1, P2, P sub r vanishes identically, it is sufficient to apply the theorems of Pascal and Desargues. Consequently, we see that every proposition relative to points of intersection in the geometry in question must always, by the aid of suitably constructed auxiliary points and straight lines, turn out to be a combination of the theorems of Pascal and Desargues. Hence, for the proof of the validity of a theorem relating to points of intersection, we need not have recourse to the theorems of congruence. End of section 35. Chapter 7, Section 36, of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 7. Geometrical Constructions Based Upon Axioms 1 through 5. Section 36. Geometrical constructions by means of a straight edge and a transferer of segments. Suppose we have given a geometry of space in which all of the axioms 1 through 5 are valid. For the sake of simplicity, we shall consider in this chapter a plane geometry, which is contained in this geometry of space, and shall investigate the question as to what elementary geometrical constructions may be carried out in such a geometry. Upon the basis of axioms of group 1, the following constructions are always possible. Problem 1. To join two points with a straight line, and to find the intersection of two straight lines, the lines not being parallel. Axiom 3 renders possible the following construction. Problem 2. Through a given point, to draw a parallel to a given straight line. By the assistance of the axioms 4 of congruence, it is possible to lay off segments and angles. That is to say, in the given geometry, we may solve the following problems. Problem 3. To lay off from a given point, upon a given straight line, a given segment. Problem 4. To lay off on a given straight line a given angle, or what is the same thing, to construct a straight line which shall cut a given straight line at a given angle. It is impossible to make any new constructions by the addition of the axioms of groups 2 and 5. Consequently, when we take into consideration merely the axioms of groups 1 through 5, All of those constructions, and only those, are possible, which may be reduced to the problems 1 through 4 given above. We will add to the fundamental problems 1 through 4 also the following. Problem 5, to draw a perpendicular to a given straight line. We see at once that this construction can be made in different ways by means of problems 1 through 4. In order to carry out the construction in problem 1, we need to make use of only a straight edge. An instrument which enables us to make the construction in problem 3 we will call a transferer of segments. We shall now show that problems 2, 4, and 5 can be reduced to the constructions in problems 1 and 3, and consequently all of the problems 1 through 5 can be completely constructed by means of a straight edge and a transferer of segments. We arrive then at the following result. Theorem 40. Those problems in geometrical construction which may be solved by the assistance of only the axioms 1 through 5 can always be carried out by the use of the straight edge and the transferer of segments. Proof. In order to reduce problem 2 to the solution of problems 1 and 3, we join the given point P with any point A of the given straight line and produce PA to C, making AC equal PA. Then join C with any other point B of the given straight line and produce CB to Q, making BQ equal CB. The straight line PQ is the desired parallel. We can solve problem 5 in the following manner. Let A be an arbitrary point of the given straight line. Then upon this straight line, lay off in both directions from A the two equal segments AB and AC. Determine upon any two straight lines passing through the point A the points E and D so that the segments AD and AE will equal AB and AC. Suppose the straight lines BD and CE intersect in F, and the straight lines BE and CD intersect in H. FH is then the desired perpendicular. In fact, the angles BDC and BEC, being inscribed in a semicircle having the diameter BC, are both right angles, and hence, according to the theorem relating to the point of intersection of the altitudes of a triangle, the straight lines FH and BC are perpendicular to each other. Moreover, we can easily solve problem 4 simply by the drawing of straight lines and the laying off of segments. We will employ the following method, which requires only the drawing of parallel lines and the erection of perpendiculars. Let beta be the angle to be laid off and A its vertex. Draw through A straight line L parallel to the given straight line, upon which we are to lay off the given angle beta. From an arbitrary point B of one side of the angle beta, let fall a perpendicular upon the other side of this angle, and also one upon L. Denote the feet of these perpendiculars by D and C respectively. The construction of these perpendiculars is accomplished by means of problems 2 and 5. Then let fall from A perpendicular upon CD, and let its foot be denoted by E. According to the demonstration given in section 14, the angle CAE equals beta. Consequently, the construction in 4 is made to depend upon that of 1 and 3, and with this our proposition is demonstrated. End of section 36. Chapter 7, Section 37 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jem Nitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 7. Geometrical Constructions Based Upon Axioms 1 through 5. Section 37. Analytical Representation of the Coordinates of Points which can be so constructed. Besides the elementary geometrical problems considered in Section 36, there exists a long series of other problems whose solution is possible by the drawing of straight lines and the laying off of segments. In order to get a general survey of the scope of the problems which may be solved in this manner, let us take as the basis of our consideration a system of axes in rectangular coordinates, and suppose that the coordinates of the points are, as usual, represented by real numbers or by functions of certain arbitrary parameters. In order to answer the question in respect to all the points capable of such construction, we employ the following considerations. Let a system of definite points be given. Combine the coordinates of these points into a domain R. This domain contains, then, certain real numbers and certain arbitrary parameters P. Consider now the totality of points capable of construction by the drawing of straight lines and the laying off of definite segments, making use of the system of points in question. We will call the domain formed by the coordinates of these points omega of R, which will then contain real numbers and functions of the arbitrary parameters P. The discussion in Section 17 shows that the drawing of straight lines and of parallels amounts, analytically, to the addition, subtraction, multiplication, and division of segments. Furthermore, the well-known formula given in Section 9 for a rotation shows that the laying off of segments upon a straight line does not necessitate any other analytical operation than the extraction of the square root of the sum of the squares of two segments whose bases have been previously constructed. Conversely, in consequence of the Pythagorean theorem, we can always construct by the aid of a right triangle the square root of the sum of the squares of two segments by the mere laying off of segments. From these considerations, it follows that the domain omega of R contains all of those and only those real numbers and functions of the parameters P which arise from the numbers and parameters in R by means of a finite number of applications of the 5 operations, namely the 4 elementary operations of arithmetic and, in addition, the 5th operation of extracting the square root of the sum of two squares. We may express this result as follows. Theorem 41. The problem in geometrical construction is, then, possible of solution by the drawing of straight lines and the laying off of segments, that is to say, by the use of the straight edge and the transferer of segments, when and only when, by the analytical solution of the problem, the coordinates of the desired points are such functions of the coordinates of the given points as may be determined by the rational operations and, in addition, the extraction of the square root of the sum of two squares. From this proposition, we can at once show that not every problem which can be solved by the use of a compass can also be solved by the aid of a transferer of segments and a straight edge. For the purpose of showing this, let us consider again that geometry which was constructed in Section 9 by the help of the domain omega of algebraic numbers. In this geometry, there exist only such segments as can be constructed by means of a straight edge and a transferer of segments, namely the segments determined by the numbers of the domain omega. Now, if omega is a number of the domain omega, we easily see from the definition of omega that every algebraic number conjugate to omega must also lie in omega. Since the numbers of the domain omega are evidently all real, it follows that it can contain only such real algebraic numbers as have their conjugates also real. Let us now consider the following problem, namely, to construct a right triangle having the hypotenuse 1 and one side the absolute value of the square root of 2 minus 1. The algebraic number, the square root of the quantity 2 times the absolute value of the square root of 2 minus 2, which expresses the numerical value of the other side, does not occur in the domain omega, since the conjugate number, the square root of the quantity negative 2 times the absolute value of the square root of 2 minus 2, is imaginary. This problem is, therefore, not capable of solution in the geometry in question, and hence cannot be constructed by means of a straight edge and a transferer of segments, although the solution by means of a compass is possible. End of section 37. Chapter 7, Section 38 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 7. Geometrical Constructions Based Upon Axioms 1 through 5. Section 38. The representation of algebraic numbers and of integral rational functions as sums of squares. The question of the possibility of geometrical constructions by the aid of a straight edge and a transferer of segments necessitates, for its complete treatment, particular theorems of an arithmetical and algebraic character, which, it appears to me, are themselves of interest. Since the time of Fermat, it has been known that every positive integral rational number can be represented as the sum of 4 squares. This theorem of Fermat permits the following remarkable generalization. Definition. Let K be an arbitrary number field, and let M be its degree. We will denote by K prime, K double prime, K to the M minus 1 prime, the M minus 1 number fields conjugate to K. If among the M fields, K, K prime, K double prime, K to the M minus 1 prime, there is one or more formed entirely of real numbers, then we call these fields real. Suppose that the fields K, K prime, K to the S minus 1 prime are such. A number alpha of the field K is called in this case totally positive in K whenever the S numbers conjugate to alpha contained respectively in K, K prime, K double prime, K to the S minus 1 prime are all positive. However, if in each of the M fields, K, K prime, K double prime, K to the M minus 1 prime, there are also imaginary numbers present, we will call every number alpha in K totally positive. We have then the following proposition. Theorem 42. Every totally positive number in K may be represented as the sum of 4 squares, whose bases are integral or fractional numbers of the field K. The demonstration of this theorem presents serious difficulty. It depends essentially upon the theory of relatively quadratic number fields, which I have recently developed in several papers. We will here call attention only to that proposition in this theory, which gives the condition that a ternary Diophantine equation of the form alpha psi squared plus beta eta squared plus gamma zeta squared equals 0 can be solved when the coefficients alpha, beta, gamma are given numbers in K, and xi, eta, zeta are the required numbers in K. The demonstration of Theorem 42 is accomplished by the repeated application of the proposition just mentioned. From Theorem 42 follow a series of propositions concerning the representation of such rational functions of a variable with rational coefficients as never have negative values. I will mention only the following theorem, which will be of service in the following sections. Theorem 43. Let f of x be an integral rational function of x whose coefficients are rational numbers and which never become negative for any real value of x. Then f of x can always be represented as the quotient of two sums of squares of which the bases are all integral rational functions of x with rational coefficients. Proof. We will denote the degree of the function f of x by m, which, in any case, must evidently be even. When m equals 0, that is to say, when f of x is a rational number, the validity of Theorem 43 follows immediately from Fermat's theorem concerning the representation of a positive number as the sum of four squares. We will assume that the proposition is already established for functions of degree 2, 4, 6, m-2, and show in the following manner its validity for the case of a function of the mth degree. Let us, first of all, consider briefly the case where f of x breaks up into the product of two or more integral functions of x with rational coefficients. Suppose p of x to be one of those functions contained in f of x, which itself cannot be further decomposed into a product of integral functions having rational coefficients. It then follows at once from the definite character which we have given to the function f of x that the factor p of x must either appear in f of x to an even degree, or p of x must be itself definite, that is to say, must be a function which never has negative values for any real values of x. In the first case, the quotient f of x divided by the quantity p of x squared, and in the second case, both p of x and f of x divided by p of x are definite, and these functions have an even degree less than m. Hence, according to our hypothesis, in the first case, f of x divided by the quantity p of x squared, and in the last case, p of x and f of x divided by p of x may be represented as the quotient of the sum of squares of the character mentioned in Theorem 43. Consequently, in both of these cases, the function f of x admits of the required representation. Let us now consider the case where f of x cannot be broken up into the product of two integral functions having rational coefficients. The equation f of theta equals 0 defines, then, a field of algebraic numbers, k of theta of the mth degree, which, together with all their conjugate fields, are imaginary. Since, according to the definition given just before the statement of Theorem 42, each number given in k of theta, and hence also -1, is totally positive in k of theta, it follows from Theorem 42 that the number -1 can be represented as a sum of the squares of four definite numbers in k of theta. Let, for example, -1 equal alpha squared plus beta squared plus gamma squared plus delta squared, equation 1, where alpha, beta, gamma, delta are integral or fractional numbers in k of theta. Let us put alpha equal a sub 1 theta to the m minus 1 power plus a sub 2 theta to the m minus 2 power plus plus a sub m equals phi of theta. Beta equals b sub 1 theta to the m minus 1 power plus b sub 2 theta to the m minus 2 power plus plus b sub m equal to psi of theta. Gamma equals c sub 1 theta to the m minus 1 power plus c sub 2 theta to the m minus 2 power plus plus c sub m equals chi of theta. Theta equals d sub 1 theta to the m minus 1 power plus d sub 2 theta to the m minus 2 power plus plus d sub m equals rho of theta, where a sub 1, a sub 2, a sub m, d sub 1, d sub 2, d sub m are the rational numerical coefficients, and phi of theta, psi of theta, chi of theta, rho of theta, the integral rational functions in question, having the degree m minus 1 in theta. From equation 1, we have 1 plus the quantity phi of theta squared plus the quantity psi of theta squared plus the quantity chi of theta squared plus the quantity rho of theta squared equals 0. Because of the irreducibility of the equation f of x equals 0, the expression f of x equals 1 plus the quantity phi of theta squared plus the quantity psi of theta squared plus the quantity chi of theta squared plus the quantity rho of theta squared represents necessarily an integral rational function of x which is divisible by f of x. F of x is, then, a definite function of the degree, the quantity 2m minus 2, or lower. Hence, the quotient f of x divided by f of x is a definite function of the degree m minus 2, or lower, in x, having rational coefficients. Consequently, by the hypothesis we have made, f of x divided by f of x can be represented as the quotient of two sums of squares of the kind mentioned in Theorem 43, and since f of x is itself such a sum of squares, it follows that f of x must also be a quotient of two sums of squares of the required kind. The validity of Theorem 43 is accordingly established. It would perhaps be difficult to formulate and to demonstrate the corresponding proposition for integral functions of two or more variables. However, I will here merely remark that I have demonstrated in an entirely different manner the possibility of representing any definite integral rational function of two variables as the quotient of sums of squares of integral functions upon the hypothesis that the functions represented may have as coefficients not only rational but any real numbers. End of section 38. Chapter 7, Section 39 of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Chapter 7. Geometrical Constructions Based Upon Axioms 1 through 5. Section 39. Criterion for the possibility of a geometrical construction by means of a straight edge and a transferer of segments. Suppose we have given a problem in geometrical construction which can be effected by means of a compass. We shall attempt to find a criterion which will enable us to decide, from the analytical nature of the problem and its solutions, whether or not the construction can be carried out by means of only a straight edge and a transferer of segments. Our investigation will lead us to the following proposition. Theorem 44. Suppose we have given a problem in geometrical construction which is of such a character that the analytical treatment of it enables us to determine uniquely the coordinates of the desired points from the coordinates of the given points by means of the rational operations and the extraction of the square root. Let n be the smallest number of square roots which suffice to calculate the coordinates of the points. Then, in order that the required construction shall be possible by the drawing of straight lines and the laying off of segments, it is necessary and sufficient that the given geometrical problem shall have exactly 2 to the n real solutions for every position of the given points, that is to say, for all values of arbitrary parameter expressed in terms of the coordinates of the given points. Proof. We shall demonstrate this proposition merely for the case where the coordinates of the given points are rational functions having rational coefficients of a single parameter p. It is at once evident that the proposition gives a necessary condition. In order to show that it is also sufficient, let us assume that it is fulfilled, and then, among the n square roots, consider that one which, in the calculation of the coordinates of the desired points, is first to be extracted. The expression under this radical is a rational function f sub 1 of p having rational coefficients of the parameter p. This rational function cannot have a negative value for any real value of the parameter p, for otherwise the problem must have imaginary solutions for certain values of p, which is contrary to the given hypothesis. Hence, from Theorem 43, we conclude that f sub 1 of p can be represented as a quotient of the sum of squares of integral rational functions. Moreover, the formulae, the square root of a squared plus b squared plus c squared equals the square root of the quantity, the square root of a squared plus b squared squared plus c squared. The square root of a squared plus b squared plus c squared plus d squared equals the square root of the quantity, the square root of a squared plus b squared plus c squared squared plus d squared. Show that, in general, the extraction of the square root of a sum of any number of squares may always be reduced to the repeated extraction of the square root of the sum of 2 squares. If now we combine this conclusion with the preceding results, it follows that the expression the square root of f sub 1 of p can certainly be constructed by means of a straight edge and a transferer of segments. Among the n square roots, consider now the second one to be extracted in the process of calculating the coordinates of the required points. The expression under this radical is a rational function f sub 2 of p, the square root of f sub 1 of the parameter p and the square root first considered. This function f sub 2 can never be negative for any real arbitrary value of the parameter p, and for either sine of the square root of f sub 1. For otherwise, among the 2 to the n solutions of our problem, there would exist for certain values of p also imaginary solutions, which is contrary to our hypothesis. It follows, therefore, that f sub 2 must satisfy a quadratic equation of the form f sub 2 squared minus phi sub 2 of p f sub 2 plus psi sub 1 of p equals 0, where phi sub 1 of p and psi sub 1 of p are, necessarily, such rational functions of p as have rational coefficients and, for real values of p, never become negative. From this equation we have f sub 2 equal the quantity f sub 2 squared plus psi sub 1 of p divided by phi sub 1 of p. Now, according to theorem 43, the functions phi sub 1 of p and psi sub 1 of p must again be the quotient of the sums of squares of rational functions. And, on the other hand, the expression f sub 2 may be, from the above considerations, constructed by means of a straight edge and a transferer of segments. The expression found for f sub 2 shows, therefore, that f sub 2 is a quotient of the sum of squares of functions which may be constructed in the same way. Hence, the expression, the square root of f sub 2, can also be constructed by means of a straight edge and a transferer of segments. Just as with the expression f sub 2, any other rational function, phi sub 2 of p comma square root of f sub 1 of p and square root of f sub 1 may be shown to be the quotient of two sums of squares of functions which may be constructed, provided this rational function phi sub 2 possesses the property that for real values of the parameter p and for either sine of the square root of f sub 1, it never becomes negative. This remark permits us to extend the above method of reasoning in the following manner. Let f sub 3 of p, comma, the square root of f sub 1, comma, the square root of f sub 2 be such an expression as depends in a rational manner upon the three arguments p, square root of f sub 1, square root of f sub 2, and of which, in the analytical calculation of the coordinates of the desired points, the square root is the third to be extracted. As before, it follows that f sub 3 can never have negative values for real values of p, and for either sine of the square root of f sub 1 and the square root of f sub 2. This condition of affairs shows again that f sub 3 must satisfy a quadratic equation of the form f sub 3 squared minus phi sub 2 of p comma the square root of f sub 1 times f sub 3 minus psi sub 2 of p comma the square root of f sub 1 equals 0, where phi sub 2 and psi sub 2 are such rational functions of p and the square root of f sub 1 as never become negative for any real value of p and either sine of the square root of f sub 1. But according to the preceding remark, the functions phi sub 2 and psi sub 2 are the quotients of two sums of squares of functions which may be constructed, and hence it follows that the expression f sub 3 equal to the quantity f sub 3 squared plus psi sub 2 of p comma square root of f sub 1 all divided by phi sub 2 of p comma the square root of f sub 1 is likewise possible of construction by aid of a straight edge and a transferer of segments. The continuation of this method of reasoning leads to the demonstration of Theorem 44 for the case of a single parameter p. The truth of Theorem 44 for the general case depends upon whether or not Theorem 43 can be generalized in a similar manner to cover the case of two or more variables. As an example of the application of Theorem 44, we may consider the regular polygons which may be constructed by means of a compass. In this case, the arbitrary parameter p does not occur, and the expressions to be constructed all represent algebraic numbers. We easily see that the criterion of Theorem 44 is fulfilled, and consequently, it follows that the above-mentioned regular polygons can be constructed by the drawing of straight lines and the laying off of segments. We might deduce this result also directly from the theory of the division of the circle, Kreisteilung. Concerning the other known problems of construction in the elementary geometry, we will here only mention that the problem of Malfatti may be constructed by means of a straight edge and a transferer of segments. This is, however, not the case with the contact problems of Apollonius. End of section 39. Conclusion of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Conclusion. The preceding work treats essentially the problems of the Euclidean geometry only. That is to say, it is a discussion of the questions which present themselves when we admit the validity of the axiom of parallels. It is nonetheless important to discuss the principles and the fundamental theorems when we disregard the axiom of parallels. We have thus excluded from our study the important question as to whether it is possible to construct a geometry in a logical manner without introducing the notion of the plane and the straight line by means of only points as elements, making use of the idea of groups of transformations or employing the idea of distance. This last question has recently been the subject of considerable study due to the fundamental and prolific works of Sophus Lee. However, for the complete elucidation of this question, it would be well to divide into several parts the axiom of Lee that space is a numerical multiplicity. First of all, it would seem to me desirable to discuss thoroughly the hypothesis of Lee that functions which produce transformations are not only continuous, but may also be differentiated. As to myself, it does not seem to me probable that the geometrical axioms included in the condition for the possibility of differentiation are all necessary. In the treatment of all questions of this character, I believe the methods and principles employed in the preceding work will be of value. As an example, let me call attention to an investigation undertaken at my suggestion by Mr. Dane, and which has already appeared. In this article, he has discussed the known theorems of Legendre concerning the sum of the angles of a triangle, in the demonstration of which that geometer made use of the idea of continuity. The investigation of Mr. Dane rests upon the axioms of connection, of order, and of congruence, that is to say, upon the axioms of groups 1, 2, 4. However, the axiom of parallels and the axiom of Archimedes are excluded. Moreover, the axioms of order are stated in a more general manner than in the present work, and in substance as follows. among 4 points A, B, C, D of a straight line, there are always 2, for example, A, C, which are separated from the other 2, and conversely. 5 points A, B, C, D, E upon a straight line may always be so arranged that AC shall be separated from BE and from BD. Consequently, AD are always separated from BE and from CE, etc. The elliptic geometry of Riemann, which we have not considered in the present work, is in this way not necessarily excluded. Upon the basis of the axioms of connection, order, and congruence, that is to say, the axioms 1, 2, 4, we may introduce, in the well-known manner, the elements called ideal points, ideal straight lines, and ideal planes. Having done this, Mr. Dane demonstrates the following theorem. If, with the exception of the straight line T and the points lying upon it, we regard all of the straight lines and all of the points, ideal or real, of a plane as elements of a new geometry, we may then define a new kind of congruence so that all of the axioms of connection, order, and congruence, as well as the axiom of Euclid, shall be fulfilled. In this new geometry, the straight line T takes the place of the straight line at infinity. This Euclidean geometry, superimposed upon the non-Euclidean plane, may be called a pseudo-geometry, and the new kind of congruence a pseudo-congruence. By aid of the preceding theorem, we may now introduce an algebra of segments relating to the plane and depending upon the developments made in section 15, pages 29 through 31. This algebra of segments permits the demonstration of the following important theorem. If in any triangle whatever the sum of the angles is greater than, equal to, or less than 2 right angles, then the same is true for all triangles. The case where the sum of the angles is equal to 2 right angles gives the well-known theorem of Legendre. However, in his demonstration, Legendre makes use of continuity. Mr. Dane then discusses the connection between the 3 different hypotheses relative to the sum of the angles and the 3 hypotheses relative to parallels. He arrives in this manner at the following remarkable propositions. Upon the hypothesis that through a given point we may draw an infinity of lines parallel to a given straight line, it does not follow, when we exclude the axiom of Archimedes, that the sum of the angles of a triangle is less than 2 right angles, but, on the contrary, this sum may be A greater than 2 right angles, or B equal to 2 right angles. In order to demonstrate part A of this theorem, Mr. Dane constructs a geometry where we may draw through a point an infinity of lines parallel to a given straight line, and where, moreover, all of the theorems of Riemann's elliptic geometry are valid. This geometry may be called non-Legendrian, for it is in contradiction with that theorem of Legendre, by virtue of which the sum of the angles of a triangle is never greater than 2 right angles. From the existence of this non-Legendrian geometry, it follows at once that it is impossible to demonstrate the theorem of Legendre just mentioned without employing the axiom of Archimedes, and in fact Legendre made use of continuity in his demonstration of this theorem. For the demonstration of case B, Mr. Dane constructs a geometry where the axiom of parallels does not hold, but where, nevertheless, all of the theorems of the Euclidean geometry are valid. Then we have the sum of the angles of a triangle equal to 2 right angles. there exist also similar triangles, and the extremities of the perpendiculars having the same length and their bases upon a straight line all lie upon the same straight line, etc. The existence of this geometry shows that, if we disregard the axiom of Archimedes, the axiom of parallels cannot be replaced by any of the propositions which we usually regard as equivalent to it. This new geometry may be called a semi-Euclidean geometry. As in the case of the non-Legendre geometry, it is clear that the semi-Euclidean geometry is at the same time a non-Archimedean geometry. Mr. Dane finally arrives at the following surprising theorem. Upon the hypothesis that there exists no parallel, it follows that the sum of the angles of a triangle is greater than 2 right angles. This theorem shows that, with respect to the axiom of Archimedes, the two non-Euclidean hypotheses concerning parallels act very differently. We may combine the preceding results in the following table. This table contains 3 rows and 3 columns. The 3 rows are: the sum of the angles of a triangle is greater than 2 right angles, less than 2 right angles, equal to right angles. The column headings are: through a given point we may draw no parallels to a straight line, 1 parallel to a straight line, and infinity of parallels to a straight line. In the column, through a given point we may draw no parallels to a straight line. Greater than 2 right angles, Riemann's elliptic geometry. Less than 2 right angles, this case is impossible. Equal 2 right angles, this case is impossible. In the second column, through a given point we may draw 1 parallel to a straight line. Greater than 2 right angles, this case is impossible. Less than 2 right angles, Euclidean parabolic geometry. Equal 2 right angles, this case is impossible. In the third column, through a given point we may draw an infinity of parallels to a straight line. Greater than 2 right angles, non-Legendrian geometry. Less than 2 right angles, semi-Euclidean geometry. Equal 2 right angles, geometry of Lobachevsky, hyperbolic. However, as I have already remarked, the present work is rather a critical investigation of the principles of the Euclidean geometry. In this investigation, we have taken as a guide the following fundamental principle, namely, to make the discussion of each question of such a character as to examine at the same time whether or not it is possible to answer this question by following out a previously determined method and by employing certain limited means. This fundamental rule seems to me to contain a general law and to conform to the nature of things. In fact, whenever in our mathematical investigations we encounter a problem or suspect the existence of a theorem, our reason is satisfied only when we possess a complete solution of the problem, or a rigorous demonstration of the theorem, or indeed when we see clearly the reason of the impossibility of the success, and consequently the necessity of failure. Thus, in the modern mathematics, the question of the impossibility of solution of certain problems plays an important role, and the attempts made to answer such questions have often been the occasion of discovering new and fruitful fields for research. We recall in this connection the demonstration by Abel of the impossibility of solving an equation of the 5th degree by means of radicals, as also the discovery of the impossibility of demonstrating the axiom of parallels, and finally the theorems of Hermite and Lindemann concerning the impossibility of constructing by algebraic means the numbers e and pi. this fundamental principle, which we ought to bear in mind when we come to discuss the principles underlying the impossibility of demonstrations, is intimately connected with the condition for the purity of methods in demonstration, which in recent times has been considered of the highest importance by many mathematicians. The foundation of this condition is nothing else than a subjective conception of the fundamental principle given above. In fact, the preceding geometrical study attempts, in general, to explain what are the axioms, hypotheses, or means necessary to the demonstration of a truth of elementary geometry, and it only remains now for us to judge from the point of view in which we place ourselves as to what are the methods of demonstration which we should prefer. End of conclusion. Appendix of Foundations of Geometry by David Hilbert. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jamnitzer, with slides and illustrations at youtube.com. Foundations of Geometry by David Hilbert, translated by E. J. Townsend. Appendix. The investigations by Riemann and Helmholtz of the foundations of geometry led Lie to take up the problem of the axiomatic treatment of geometry as introductory to the study of groups. This profound mathematician introduced a system of axioms which he showed by means of his theory of transformation groups to be sufficient for the complete development of geometry. As the basis of his transformation groups, Lie made the assumption that the functions defining the group can be differentiated. Hence, in Lie's development, the question remains uninvestigated as to whether this assumption as to the differentiability of the functions in question is really unavoidable in developing the subject according to the axioms of geometry, or whether, on the other hand, it is not a consequence of the group conception and of the remaining axioms of geometry. In consequence of his method of development, Lie has also necessitated the express statement of the axiom that the group of displacements is produced by infinitesimal transformations. These requirements, as well as essential parts of Lie's fundamental axioms concerning the nature of the equation defining points of equal distance, can be expressed geometrically in only a very unnatural and complicated manner. Moreover, they appear only through the analytical method used by Lie, and not as a necessity of the problem itself. In what follows, I have therefore attempted to set up for plane geometry a system of axioms depending likewise upon the conception of a group which contains only those requirements which are simple and easily seen geometrically. In particular, they do not require the differentiability of the functions defining displacement. The axioms of the system which I set up are a special division of Lie's, or as I believe, are at once deducible from his. My method of proof is entirely different from Lie's method. I make use particularly of Cantor's theory of assemblages of points, and of the theorem of C. Jordan, according to which every closed continuous plane curve, free from double points, divides the plane into an inner and an outer region. To be sure, in the system set up by me, particular parts are unnecessary. However, I have turned aside from the further investigation of these conditions to the simple statement of the axioms, and above all, I wish to avoid the comparatively too complicated proof, and one which is not at once geometrically evident. In what follows, I shall consider only the axioms relating to the plane, although I suppose that an analogous system of axioms for space can be set up which will make possible the construction of the geometry of space in a similar manner. We establish the following convention, namely, we will understand by number plane the ordinary plane having a rectangular system of coordinates x, y. A continuous curve lying in this number plane and being free from double points and including its endpoints is called a Jordan curve. If the Jordan curve is closed, the interior of the region of the number plane bounded by it is called a Jordan region. For the sake of easier representation and comprehension, I shall, in the following investigation, formulate the definition of the plane in a more restricted sense than my method of proof requires. Namely, I shall assume that it is possible to map in a reversible single-valued manner all of the points of our geometry at the same time upon the points lying in the finite region of the number plane or upon a definite partial system of the same. Hence, each point of our geometry is characterized by a definite pair of numbers, x, y. We formulate this statement of the idea of the plane as follows. Definitions of the plane. The plane is a system of points which can be mapped in a reversible single-valued manner upon the points lying in the finite region of the number plane or upon a certain partial system of the same. To each point A of our geometry, there exists a Jordan curve in whose interior the map of A lies, and all of whose points likewise represent points of our geometry. This Jordan region is called the domain of the point A. Each Jordan region contained in a Jordan region which includes the point A is likewise called a domain of A. If B is any point in the domain of A, then this domain is at the same time called also a domain of B. If A and B are any 2 points of our geometry, then there always exists a domain which contains at the same time both of the points A and B. We will define a displacement as a reversible single-valued transformation of the plane into itself. Evidently, we may distinguish 2 kinds of reversible single-valued continuous transformations of the number plane into itself. If we take any closed Jordan curve in the number plane and think of its being transversed in a definite sense, then by such a transformation, this curve goes over into another closed Jordan curve, which is also transversed in a certain sense. We shall assume in the present investigation that it is transversed in the same sense as the original Jordan curve, when we apply a transformation of the number plane into itself, which defines a displacement. This assumption necessitates the following statement of the conception of a displacement. Definition of displacement. A displacement is a reversible, single-valued, continuous transformation of the maps of the given points upon the number plane into themselves in such a manner that a closed Jordan curve is transversed in the same sense after the transformation as before. A displacement by which the point M remains unchanged is called a rotation about the point M. In accordance with the convention setting forth the notions of plane and displacement, we set up the 3 following axioms. Axiom 1. If 2 displacements are followed out, one after the other, then the resulting map of the plane upon itself is again a displacement. We say, briefly, Axiom 1, the displacements form a group. Axiom 2, if A and M are 2 arbitrary points distinct from each other, then by a rotation about M, we can always bring A into an infinite number of different positions. If in our geometry we define a true circle as the totality of those points which arise by rotating about M, a point different from M, then we can express the statement made in Axiom 2 as follows. Axiom 2. Every true circle consists of an infinite number of points. As preliminary to Axiom 3, we make the following explanations. Let A be a definite point in our geometry, and A1, A2, A3, any infinite system of points. With the same letters, we will also denote the maps of these points upon the number plane. About the point A in the number plane, take an arbitrarily small domain alpha. If then any of the map points A sub I falls within the domain alpha, we say that there are points A sub I arbitrarily near the point A. Let A, B be a definite pair of points in our geometry, and let A1, B1, A2, B2, A3, B3, be any infinite system of pairs of points. With the same letters, we will denote the maps of these pairs of points upon the number plane. Select about each of the points A and B in the number plane an arbitrarily small domain alpha and beta respectively. If then there are pairs of points A sub I, B sub I such that A sub I falls within the domain alpha and at the same time B sub I falls within the domain beta, we say that there are segments A sub I, B sub I lying arbitrarily near the segment AB. Let A, B, C, a definite triad of points in our geometry, and let A1, B1, C1, A2, B2, C2, A3, B3, C3, be any infinite system of triads of points. With these same letters, we will also denote the maps of these triads of points upon the number plane. About each of the points A, B, C in the number plane, take an arbitrarily small domain alpha, beta, gamma, respectively. If then there are triads of points A sub I, B sub I, C sub I, such that A sub I falls in the domain alpha, and likewise B sub I in the domain beta, and C sub I in the domain gamma, then we say that there are triangles A sub I, B sub I, C sub I lying arbitrarily near to the triangle ABC. Axiom 3. If there are displacements of such a kind that triangles arbitrarily near the triangle ABC can be brought arbitrarily near the triangle A', B', C', then there always exists a displacement by which the triangle ABC goes over exactly into the triangle A', B', C'. The content of this axiom can be briefly expressed as follows. Axiom 3. The displacements form a closed system. We call special attention to the following particular cases of Axiom 3. If there are rotations about a point M of the kind that segments lying arbitrarily near the segment AB can be brought arbitrarily near the segment A', B', then there is always such a rotation about M possible by which the segment AB goes over exactly into the segment A', B'. If there are displacements of the kind that segments arbitrarily near the segments AB can be brought arbitrarily near the segment A', B', then there is always a displacement possible by which the segment AB goes over exactly into the segment A', B'. If there are rotations about the point M of the kind that points arbitrarily near the point A can be brought arbitrarily near the point A', then there is always such a rotation about M possible by which A goes over exactly into the point A prime. I now prove the following proposition. A geometry in which axioms 1 through 3 are fulfilled is either the Euclidean or the Bolyai-Lobachevskian geometry. If we wish to obtain only the Euclidean geometry, it is necessary merely to make in connection with axiom 1 the additional statement that the groups of displacements shall possess an invariant subgroup. This additional statement takes the place of the axioms of parallels. In what follows, I will briefly outline the general idea of my method of proof. Within the domain of a certain point M, construct in a particular manner a certain point configuration kk, and upon this configuration construct a certain point k. We then base our investigation upon the true circle K about M and passing through K. It may be easily shown that the true circle K is an assemblage of points which is closed and in itself dense. It constitutes, therefore, a perfect assemblage of points. The next objective point in our demonstration is to show that the true circle K is a closed Jordan curve. We do this in that we first show the possibility of a cyclical arrangement of points of the true circle K, from which it follows that we may map in a reversible, single-valued manner the points of K upon the points of an ordinary circle. Finally, we show that this map must necessarily be a continuous one. Furthermore, it follows also that the ordinary constructed point configuration kk is identical with the true circle K. Moreover, the law holds that each true circle inside of K is likewise a closed Jordan curve. We turn now to the investigation of the group of all the displacements, which, by the rotation of the plane about M, transforms a definite true circle K into itself. This group possesses the following properties. 1. Every displacement which leaves one point of K undisturbed leaves all points of K undisturbed. 2. There always exists a displacement which changes any given point of K into any other given point of K. 3. The group of displacements is a continuous one. These three properties determine completely the construction of the group of transformations of all the displacements of the true circle into itself. We set up the following proposition. The group of all of the displacements of the true circle into itself, which are rotations about M, is holoedric, isomorphic with the group of ordinary rotations of the ordinary circle into itself. Moreover, we investigate the group of displacements of all of the points of our plane by a rotation about M. The law holds that, aside from the identity, there is no rotation of the plane about M which leaves every point of the true circle undisturbed. We now see that every true circle is a Jordan curve, and deduce formulae for the transformation of that group of all rotations. Finally, the proposition easily follows that if any 2 points remain fixed by a displacement of the plane, then all points remain fixed. That is to say, the displacement is the identity. Each point of the plane may be indeed made to go over into any other point of the plane by means of a displacement. Our further important objective point is to define the idea of the true straight line in our geometry and deduce those properties of it which are necessary in the further development of geometry. First of all, the notions semi-rotation and middle of segment are defined. A segment has at most one middle, and when we know the middle of one segment, then every smaller segment possesses a middle. In order to pass judgment as to the position of the middle of a segment, we need particular propositions concerning true circles, which are mutually tangent, and indeed the question depends upon the construction of two congruent circles tangent to each other externally in one and only one point. We derive also a more general proposition concerning circles, which are tangent to each other internally, and consequently a theorem covering the special case where the circle which is tangent internally to a second passes through the center of that circle. Moreover, a sufficiently small definite segment is taken as a unit segment, and from this, by continued bisection and semi-rotation, a system of points is constructed of the kind that to each point of this system a definite number A corresponds, which is rational and has as denominator some power of 2. By setting up a law concerning this correspondence, the points of the above system are so arranged that the above laws concerning mutually tangent circles are valid. It is now shown that the points corresponding to the numbers 1/2, 1/4, 1/8, ... converge toward the point 0. This result is generalized step by step until it is finally shown that every series of points of our system converges so soon as the corresponding series of numbers converges. From what has been said, the definition of the true straight line follows as a system of points which arise from two fundamental points. If we apply repeatedly a semi-rotation, take the middle point, and add to the assemblage the points of condensation of the system of points which arises, we can then prove that the true straight line is a continuous curve, possessing no double points, and having with any other true straight line at most one point in common. Furthermore, it can be shown that the true straight line cuts each circle drawn about one of its points, and from this it follows that any two arbitrary points of the plane can always be joined by a true straight line. We see also that in our geometry the laws of congruence hold, by which, however, two triangles are proven to be congruent if they are transversed in the same sense. With regard to the position of the systems of all the true straight lines with respect to one another, there are two cases to distinguish, according as the axiom of parallels holds, or through each point there exist two straight lines which separate the straight lines which cut the given straight line from those which do not cut it. In the first case we have the Euclidean, and in the second the Bolyai-Lobachevskian geometry. End appendix. End of the Foundations of Geometry by David Hilbert, translated by E. J. Townsend.